so we are going to start the tutorial session this morning. So first, welcome to our tutorial session. Today we are going to talk about recent advances in vision foundation models. And then I feel really blessed that there are so many people coming so in this session this morning, and hope everyone will learn something or enjoy the session. So I will first give a high-level overview of the tutorial, and then I will also dig into one specific topic. And then other people, other speakers will follow up on other topics. Before going into the detail, I'd like to first have a kind of brief recap of the tutorial history that we have. So actually back then in 2020, we have our first tutorial session. And at that time, we don't have VLP, we don't have vision language pre-training. And then we focus on the task-specific VQA task. And also we are in the pandemic, right? So every conference is online. And then in 2021, we have our second version. And in this version, we mainly focus on vision language pre-training. And also we focus on vision language navigation. And then come to last year, finally we have in-person conference, right? And really I enjoyed a very good in-person conference last year. And then we have a whole one-day session. Besides talking about vision language pre-training methods for the kind of traditional image text tasks, such as image captioning and VQA, we also further enrich our tutorial with topics such as how we can perform language image pre-training for image classification, object detection, and etc. So actually we have a survey paper. So so if you are interested in those recent advances, we put an archive paper last year that is on how we can quickly say the landscape of the vision language pre-training area from the basics to recent advances, and then dig into future trends. So you must be curious then what we are here today, right? So this year actually we have a brand new design of this tutorial. The reason is actually just because things are evolving really quickly, right? And then so if we look at the archive, the topic in the multimodal field, the papers, the number of papers, they are really growing in a weekly basis. Basically every week or even every day, we can see archive paper on this topic. And then from the language modeling perspective, right, now we have so powerful ChatGPT, GPT-4 from OpenAI. We also have Palm, Bard from Google, and also Llama from Meta, right? And then from the open source community, there are so many instruction tuned versions such as Alpaca, Vincula, etc. We also have so many large language model startups. From the computer vision perspective, everyone knows them. We also, so from the community side, we also have Dino 2 Stable Diffusion, Midjourney. We also have how we can try to have some mini GPT-4, etc. So really, what's new? So this year, so basically, we want to answer the following questions. Suppose we have an image text pair. In this case, the caption of this image is a dog is running through the grass. And such data is usually widely exists from the web, right? We can mine millions, even billions of image text files from the data, and then there's really a very rich signal inside it that we can learn from. So first, we are going to talk about the image encoder, which is the foundation, maybe foundation of the foundation. So we will first discuss how we can learn an image encoder to consume visual data. And then in terms of this, we are going to answer two questions. For one is how we can learn better image representation, possibly from the image signal only or from the image text signal. For question two, we are going to talk about how we can extend the current vision model with more flexible and promptable interface. Not only we are interested in consuming visual data, we are generally also very interested in producing visual data, right? This comes to the image generation part. So the question is how we can do image generation, and we will also cover this. And then the interesting thing is we have the large language model coming into play. LM has very strong language understanding and generation capability, especially recent in instruction tuning ones, right? So here we are going to use LM as the general purpose interface, and we are going to talk about how we can train multimodal LM and how we can train multimodal experts with those LLM. So basically, this so all these questions is the ones that we are going to answer in this tutorial. Specifically, this is the agenda. In part 1, I will going to talk about visual and visual language pre-training to consume visual data. Basically, it's about how we can learn a strong image encoder. In part 2, Jianwei will talk about how we can design vision interface that is interactive and promptable. In part 3, Zhenyuan will talk about how we can produce visual data that is also aligned with human intent. In part 4, Zhenyuan will talk about how we can make a multimodal LLM that can see and chat. And finally, Lingjie will talk about how we can train those multimodal experts with large language model to unlock new capabilities. So I think without further ado, I'm going to dig into my part, which is about visual pre-training and visual language pre-training. So as we can see, there are multiple training paradigms in this area. Supervised pre-training maybe the most classical and maybe also most the powerful ones to train an image encoder from scratch. And here comes the click model, right? We can use large scale so weak supervision from the text signal to learn the image encoder. We also have contrastive learning, and actually we also have non-contrastive learning, which aims to mine the visual signals from the image. So from the image sounding. We also have masked image modeling, which mimic the spirit of BERT, but then borrow the concept from NLP to computer vision. And here, not only in those 4 training paradigms, they are independent. No, they are not. They are quite so interactive with each other. And we will also briefly talk about how the community as a whole has made progress in how the different training paradigms can be integrated together. Also, as we can, this is like a disclaimer. It's there are really a vast number of literature on this topic, and then due to the time that we have, I only select the papers that I think is interesting and surely with my own bias, and then we are going to use CLIP as the anchor point to discuss the topic. So let's first have a quick recap of the supervised learning. So the supervised learning is to map an image to a discrete label, which is associated with to a visual concept. So basically, the label is a one-hot concept. During the model training process, maybe the model doesn't learn the semantics behind it. So the prompts is usually the data sets clearly or the annotation is done in a very clean manner. But the cons is that for one, the human annotation can be very expensive, and the number of labels that you can label can be limited. But then indeed, there are also many private data sets that is it's not available from public, but they indeed exist, right, from the industry lab. For example, Google's GFT 3 billion and also Meta's Instagram data sets. And in the literature, they may also call it the so-called weakly supervised pre-training. And although mostly those signals, they are weak supervision, but actually they can be very powerful in terms of learning universal embeddings. And the supervised training paradigm has also powered architectures ranging from the classical AlexNet, ResNet to the more recent vision transformer and the stream and so many other model variants. Basically, supervised learning is the test bed for all the modern vision backbones. So here, with the concept of supervised learning, here we are So we are going to quickly introduce what is clip. I guess most of you may already know it, but then just for background knowledge, clip tries to learn image representations from the web scale, noisy text supervision. So the training is very simple, right? We just use contrastive learning, and the beauty lies in large scale pre-training. So if you only have millions of image text examples, it may not be powerful. But then if you really have billions of image text files, then your zero-shot image net can go up to more than 80%, right? And then another key property is that now we can do zero-shot. We can do zero-shot image classification. We can also do zero-shot image text retrieval. For retrieval, it's easy to understand because this is basically the pre-training task you use. But then for image classification, it's mainly due to the image classification can be formatted as a retrieval task. If you consider the labels, they are not just the one hot label, but then you consider the semantics behind the label names. So the idea is really simple, and actually the idea can be dated back to a long while ago, right? So, but then in the large scale pre-training area, the pioneering work is it's a clip and align. And here we can see data scale really matters. So models are frequently measured. Models are frequently trained with billions of image text files. And also, so basically, if you want to scale a model, there could be 3 dimensions, right? The data scale, model scale, and the bench size scale. So because it's a contrastive learning, so usually we will need a very large bench size to do a good job. So this is one quote that I quoted from the Flip paper, which is one paper from CVPR this year that I feel really agree with it. So it says, language is a stronger form of supervision than classical closed-set labels. And the language provides rich information for supervision. And then scaling is a very important factor, both in terms of model scaling and also data scaling. And especially, I think this sentence is very good. It's a clip is an outstanding example of simple algorithm that scale well. So I think really, when we have a simple algorithm, but then if it has a very good scaling property, it can really unlock many of the potentials that previous model have never been seen before. So this is CLIP basically, right? And then, so I think since the birth of CLIP, tons of follow-up works has been emerged in in archive, in CVPR, in all the conferences. So here I'm going to talk about some of the recent follow-ups that I think is interesting. So I think for one is data scaling, right? You have the image, you have the text, but then how can you further scale it up? The second ability is model design, how we can design better models out of the original clip. I'm also going to cover briefly about the objective function. Contrastive pre-training is indeed powerful, right? But then what's the other objectives people have been using? Can we get some inspiration from them? So for data scaling, I think in this year's CVPR, and then so I think there's a paper, it's called the reproducible scaling law for clip training. So basically using the open source large scale around 2 billion data sets, they can pre-train the open clip model across various scales. And then recently, another interesting paper is the data camp. So we know scale matters, especially the data scale, right? But then how we can further scale it up? Are we just scaling it up using noisy and noisier data? And I think in this paper, they propose a very nice idea is in search of the next generation image text data sets. So I think the idea is instead of fixing the data set and designing different algorithms, which is basically what we do every day. And in this paper, the authors propose to fix the clip training methods. Basically, this is the training algorithm. It's fixed. You just provide me the data set, and then the data set will just go through a fixed training methods, and then you are going to play the game of selecting the data rather than playing the game of selecting the model. So I think so by the end, the authors come up with a large scale data set that has a high performance. For example, in zero-shot ImageNet. So in terms of model design, from the image side, I think one recent interesting paper is the Flip paper. So I think in terms of training, it still use the original clip loss, and even the MIM loss is not used because later on they will show the MIM loss is basically not useful to enhance the clip model. But then the trick is, here we the authors propose to randomly mask out image patches within with a high masking ratio, and then only encoding the visible patches. So the idea is very simple and it's more like a trick, right? So given the image as your input, you are not going to encode the full image as your input, but rather you just randomly mask out the images, like what you do in MAE or in MIM, but then do the original clip training. And after doing this, the authors have shown that it doesn't hurt performance, and actually it can improve your training efficiency by a lot. So from the language side, one paper that I think is interesting is how we can enrich the language that you have been using external knowledge. And here, when we say external knowledge, it basically means the Wikipedia definition of entities or the so-called knowledge. So that, so for example, so in this figure, there's a motivating example. Maybe if you are not familiar with Japanese food, right? Maybe you don't know what is sashimi, but then if you provide a definition of sashimi, maybe you don't know the concept of sashimi, but still you can kind of know what does sashimi mean from its definition. So that if you enhance your language side, enhance your language input with such data, it can help you learn a better clip model. And actually in the small scale setting, the authors have shown that enriching alt text with entity description can enhance the performance. We can also say work to improve the interpretability, right? And here is one paper called Cell. So instead of mapping images and the text into a relatively low dimensional but dense embedding space, here we can also try to map the image and the text into a very high dimensional space. But in this high dimensional space, it is very sparse. So each dimension in the sparse embedding is a subword in a very large dictionary, basically covering your whole vocabulary. But then the weight associated to each dimension means how important. Corresponds to the weight associated with the token. So as you can see, given the original caption, so if you follow this idea from the information retrieval literature, basically you are going to learn more interpretable embedding by grounding your embedding directly to tokens, but in a sparse manner. We also have image bind. This is a very recent work, right? The idea is quite simple. It's basically now you have more than, for other modalities, it may not easy for you to scale up, but then for image text, it's really easy for you to scale up. Then how about you use the fixed pre-trained clip model, right? So basically the idea is you are going to link all the other modalities to the clip embedding space. So so actually, this basically means you don't need, so if you have a pre-trained clip embedding, you can always try to upgrade the clip model by aligning this clip embedding space to some other modalities. And then if you can do this, you can try to unlock some new capabilities that you may not be able to do before, right? And in the paper, they also show they can do, usually we do text to image generation, right? But here they can do audio to image generation. But really it's, you get an audio as input, but then due to your audio and the text, they are in the same space, then you just map your audio into an embedding, so without changing anything. And then I'm going to talk about objective function. One paper is fine-grained supervision. Besides the contrastive loss we are going to use, people have been developing how we can provide more fine-grained supervision. And in this paper, they have been shown if we trying to learn the word patch alignment during your training process, then you can enhance the performance and get a better clip model. For example, in the visualization, they show instead of just compressing image into one feature vector, text into another feature vector, and do the dot product. Here, we also propose to learn the word patch alignment so that the model kind of capture the fine-grained information. So another interesting idea is COCA, right? How about we add in a generative branch? So I think this is always what we do if you see the traditional vision language so literature, right? But then I think the key concept in this paper is that they are not just interested in VQA and image captioning, but really they want to learn the image encoder from scratch. So treating COCA as image encoder learning methods. So instead, so here they use mixed image text and image label data for pre-training, but then they add another generative branch for enhanced performance. And due to the use of the generative branch, they can also encode new capabilities such as captioning and VQA. Yeah, they similar to many other vision language model, but then the model is purely trained from scratch. You must be curious about how about we learn the image, whether we can learn image encoder from scratch just using the image captioning loss, right? And indeed it's possible. So how about using the captioning loss again? So I think the whole wave of using image text supervision, right, to learn image encoder. So I think the beginning, so I mean, if we really want to date back to the literature, it can be so dated back further, right? But recently, I think it's due to the introduction of Vortex, right? So in the Vortex paper, the authors proposed to use the COCO, although it's very small scale, it's using COCO data, but then they show using the image captioning loss, indeed can learn image encoder from scratch. But then in CLIP, the authors show contrastive pre-training is much more effective. And then in the CVPR paper, the authors also show the learned image encoder was actually, the same message, not competitive compared with CLIP. But then in the recent paper, also by Google Brain, CAP and CAPA, the authors actually argue that image captioners can be scalable vision learners too. And the captioning exhibits the same or even better scaling behavior. So I think this is also one interesting message they deliver in the paper is just using the simple image captioning objective. You can learn very good image encoder. And especially when you use such image encoder for downstream tasks that deals with multimodal fusion. Yeah. So another interesting topic that I like to briefly discuss is can CLIP be combined with other learning approaches? And this also provides us with a nice way to connect with other learning approaches. So we will first briefly talk about supervised learning. So not only we have separation from text, we also have separation from the label, right? And I think for supervised learning, the problem is you can learn discriminative visual representation, but the con is that you have only limited visual concepts. But on the other hand, for CLIP kind of model, you have broad semantic coverage, but your representation may not be discriminative enough. And in this UniCell paper, the authors propose a principled way to use both image label and image text data together for learning a strong image encoder. And the scale-up version is the Florence model. Besides that, we can also say there are some other methods trying to do that, right? Because your image encoder can learn a very discriminative representation. So in the LIT paper, the authors basically propose you first pre-train the image encoder using image text data. And in this scale, it can be GFT 3 billion. But then based on this frozen image encoder, then you can make the model open vocabulary. by just learning an additional text power. So basically, the idea is just to teach a text model to read out a good representation from a pre-trained image encoder to new tasks. And then by doing this, they also show much improved performance. And recently, we also have the MOFAT paper. So trying to learn image representation from noisy entity annotated images. So here, the authors proposed the I2E data. And I think this is the largest data set of its kind in terms of the number of entities they have been using. So as you can see, the authors have collected 1 billion images with 2 million entities. So the message is that if you want to do supervised pre-training, then you'd better you have a large number of labels that you want to predict from. So going beyond the ImageNet 1K and possibly ImageNet 22K, right? So by using such data sets, the authors show that on the image-to-image retrieval benchmark, which can have wider industry use, the performance can be improved a lot compared with the original clip model. And this is some of the example of the I2E data set. So in terms of learning, it's also very simple. For supervised learning, right? It's basically you treat the entities as labels. And the only difference is now you have 2 million labels rather than, for example, 20K labels. So though this is a very classical method, it's very effective for image-to-image retrieval tasks, actually. And then for clip, we can treat entity name as free-form text, as we usually do for all the clip model training. And then we can also enrich them with entity description. So this is some idea very similar to Paylet, but now in a much larger scale. And then they also combine supervised pre-training and clip for multitasking, and they show strong performance to learn image backbone with performance so even better than the Dino V2 paper. So I think the combination of clip and the supervised pre-training is positive, right? Then how about we combine clip with some of, so for example, image-only contrastive learning methods, right? So I think we can have first have a very high-level overview of so what is contrastive learning of visual representation, if you are not familiar. So just in case. So I think CVPR is a kind of a very classical paper, right, to do such a job. So basically, all the papers they are following the same paradigm. It's basically you have you given one image, right? Then you are going to generate two different views of the same image, and then you have a base encoder followed by a projection head, which is trained to maximize the agreement using the contrastive loss. And then the projection head will be thrown away for downstream tasks. And then the methods can also, due to the use of contrastive loss, you can always try to connect with mutual information maximization literature. But then, so as you can see, this is basically all the same framework for all the so image-only contrastive learning, right? You have one input image, then get a different augmentation. Then you are trying to learn a contrastive model from it. But then the caveat is you will need a very large bench size, for example, for CVPR training, or you will need a very large memory bank, for example, for the MOCA training, right? And indeed, in the literature, people gradually find that we can relieve the dependency on negative examples. For example, the use of negatives can be replaced by asymmetric architectures, dimension decorrelation, and also can be replaced by clustering. So basically, instead of using negatives as the regularization, people have been trying to use different methods to provide such regularization so that the model will not just learn a trivial solution, right? And then the left is one example from the Simpson paper, and on the right is the Dino. And the Dino is basically using the self-distillation idea. So, but as you can see, no matter how the different training algorithms so it's a design, you will always have one input X And this one input X will become two inputs, which is X1 and X2 here. And this X1 and X2, they will go into an encoder. And this encoder can be the same, or can be different, or can be a momentum contrast, or can be an exponential moving average, right? And usually you will have a stop gradient operator on one side, or either you do not have it, but then you need to add other regularization to make it work. Okay, so this is the very quick overview of the contrastive learning, right? But then how we can combine together with the clip kind of training. So I think one paper is the D-clip paper, right? The high-level message is supervision can exist everywhere. So they propose to enhance the clip training with self-supervised learning on each modality. For example, in the image side, they use in the SIM-SAM loss as well. And then we also have the sleep paper, right? And the idea is even simpler. It's simply combine SIM-CLR and the clip for model training. And by doing this, in an academic setup, they show they can have better zero-shot transfer and linear block performance. We can also try to make clip non-contrastive, right? As the name suggests, the contrastive language image pre-training. But then can we similar like how the non-contrastive learning methods have been used for image-only self-supervised learning? So here, can we explore the idea of making the clip model non-contrastive? And actually the answer is yes, right? So without using negatives, we can ensure non-trivial solution while some regularization term. And this is some regularization term from this paper. So as you can see in the clip model, right, you have the positive path, and then you also have the negative path to make the model learn general representation. But in the unclip setup, the model will only using a positive path to learn such such model. But then there's also some bad news is that only using so different from the image-only literature, only using unclip or the non-contrastive clip is not enough for strong performance, and it needs to be used together with the original clip. So basically, the proposed X clip in their paper is a combination of clip and unclip. It's like you are using an additional unclip as the regularization term for you to learn a better performance. Okay, then this is good, right? Since the message is also positive. So then I'm going to briefly discuss master image modeling. So I think BATE is one important work in this field, right? So the high-level idea is can we perform BERT-like pre-training of image transformer, just like what we do in BERT literature? So as you can see from the figure, before the pre-training, we need to learn an image tokenizer, which can be the VQVE or VQGAN, right? And then this we are trying to tokenize your input image into a set of discrete visual tokens. And these discrete visual tokens will be used as your training target. To learn the image encoder. So the similar approaches have also been used for image generation, such as DAE and PATI. And the idea is you will randomly masking the image batches, and then you will pre-train the model to predict, as I just said, pre-train the model to predict those masked visual tokens. Actually, it can also be understood as knowledge distillation, right? As you can see, there's a image tokenizer, and this image tokenizer is kind of the teacher. And you also have the beta encoder, and this beta encoder is kind of the student. But it's only now the student is doing a much harder job, because your student can only see partial image instead of the whole image as your input. Many people say MIM is more like a fine-tuning method because it can show strong fine-tuning performance, right? Compared with so starting from scratch. But it's kind of seems not like a representation learning methods due to the model itself cannot provide a single global image representation, right? So it can be good for fine-tuning. And then later work, the famous one, right? The MAE, they show, oh, you don't need to use discrete tokenizer. Why not using pixel directly? And actually, it can indeed work, right? You just randomly mask out the images, and then your encoder will apply on those visible patches, and then it works, right? And then besides using pixels, why not using other features? And in the mask field paper, they also have shown in actually many other so features can also be used as target as well. And one special one they find is so work is the so-called very traditional hop feature. So as I just mentioned, there could be some potential problem with the naive MIM. The first one is the scaling probably may not be that clear compared with clip. So MIM is very scalable in terms of the model size. You can train the model from small size goes to 1 billion or even larger. But then from the data, data scaling perspective, usually those models are pre-trained on the ImageNet 21K data set, right? They did not go even further, or when they go even further, they did not see some meaningful improvement. So I think that indeed there are some recent work trying to study whether MIM is also scalable in terms of the data size. But I think the conclusion is still not conclusive yet. And so at least those models do not go to billion scale images. So I think MIM is good for model fine-tuning, but since not learn a global image representation, although there are some remedies such as the iBot paper is basically or roughly, what did I do? Yeah, that's like a surprise. So for example, iBot is a combination of the Dino and also the bait paper and the bait idea, right? And then this idea also be adopted to the Dino V2 paper. So indeed, in the paper they show the bait itself cannot learn a global image representation, right? As you can see, the red box, the linear probe performance is actually quite low, right? But then, if you can see from the left, if you trying to enforce to push your information inside the sales token, then the model can learn global information. Okay, so before talking about the clip and the combination of clip and the masked image modeling, actually we talked about the combination of image-only contrastive learning and masked image modeling. So then can clip and MIM can combine together? So I think there could be two kinds of combination, right? For one is a shallow combination, right? Shallow combination is a kind of you use these two models interactively, or actually it turns out the image feature from clip can be very useful or can be a very good target for MIM training. Partially is due to, because now the target is clip feature, right? So the clip feature can capture the semantics that is missing in the MIM training. This is one approach. It's the MVP paper, ECCV last year. They for the model that you are going to learn, right? So they will directly regress to the clip feature. And then in the V2 paper, instead of directly trying to regress the clip feature, the authors using another idea, but basically it's similar. It's you are trying to compress your clip information into your visual tokenizer. And then after you get this new set of visual tokenizer, you can do the weight training as usual. So basically it's another way of using clip feature into your model training. But then you must be curious, then the real, so really the whole training pipeline is really very long, right? Yeah, and so I think this approach is further kind of popularized by the EVA series of work. In the EVA paper, they first use clip to train MIM, and then in their later work, they use the clip as the initialization to train the clip model. And then finally they say, hey, this is an alternative learning, right? So it's like you have your clip model, which can be used to train your MIM model using clip as the target, right? And then on the other hand, after you train the MIM, you can use the MIM as the initialization to train your clip model. And then, as you can see, due to MIM is very good at model fine-tuning, right? So the fine-tuning can be used for hardcore task if you care about fine-tuning performance, right? But then the clip model can be used for zero-shot task you may be interested in. And then in this paper, they showed these two can have a kind of very good synergy so between them, so which is nice. As you can see, this is a kind of a shallow interaction between CLIP and MIM. So I think in the community, they also work trying to investigate, can we have a deeper integration? So I believe some of them come into papers, and some of them due to its negative results, right? So it's never into a paper. But indeed, since currently it's more like a negative answer. So in this paper, masked autoencoding does not help natural language supervision at the scale. They also show at a small scale, since MIM is useful to help CLIP, but if you do it in a larger scale, this doesn't help. This is also a CVPR paper this year. And actually in the flip paper, in the very beginning I mentioned, right? They also show this is negative. So by the end, they didn't use MIM. So by the end, the authors didn't use MIM, right? And then reframe their story to say I can improve CLIP, so training efficiency by randomly masking out the image patches, right? But then if you dig into the paper, in their ablation study, they indeed show in this training paradigm, seems naively combine them together will not lead to a stronger backbone. So I think I'm going to conclude. But before conclude, indeed, CLIP and MIM, they are not positive, but BERT and MIM, they are positive, right? So this is, you can try to combine BERT and the BERT together. This is intuitive, right? Because they are both just to do masking, right? And I think I have checked it all, the points here. So besides backbone, we also have many other backbone, right? We didn't discuss, but then really, we don't have that much time, but really we have a lot of backbones other than VIT, such as the ConvNext and the InterImage. And here come to a high-level summary. So in this brief part of my tutorial, I centered around the CLIP, and we discussed how we can train a strong image backbone as foundation. And actually, we only focus on image level pre-training. We didn't touch region level pre-training or pixel level pre-training, such as CLIP, SAM, XDecode, etc. Because actually, they typically will use a pre-trained image encoder as a first hand, right? So, so the image encoder pre-training is like the foundation of the foundation. If you consider SAM, XDecoder, CLIP as foundation, right? And it's just some observation. We can see some high-level principle. Scaling, contrasting, masking is something like the general design principle behind all these methods. And for future challenges, really, I don't know what to say, but then, yeah, I'm just trying to list some. How to further scale up, scale it up, especially in terms of model sets, right? Because we know vision foundation models typically are much smaller than the language counterparts. Maybe also new model training paradigm. But then if you want to have a new model training paradigm to be popular, it's better to be simple. But then it also means it's so very difficult to design such an algorithm. Also, how we can perform unified image region pixel level pre-training, which I will leave to my next speaker. It's also very challenging to say how we can extend the current vision model with more flexible and comfortable interface, which my next speaker will also talk about it. Finally, how we can train vision foundation models with more innovative data, right? If we check about the GPT-4 paper, right? If you provide a scanned PDF summary of one paper, the GPT-4 model can even just summarize the paper for you, right? So how this kind of capabilities can emerge? But then if we just use natural images, this can never happen, right? But then how can we? I don't know. But then how can we train vision backbone with more innovative data? This is something that I'm interested in. But then till now, although all the papers I have been talking about is all about this small point, is how we can consume visual data. And then the other speakers will talk about the rest. And yeah, so I think I will stop here, and thank you.
So yeah, so all right, so yeah, thanks Juzer for the great talk. So go back to this picture. Now that we know how to learn this kind of general visual representation from different type of learning methodologies like supervised learning, like masking. Sorry. Oh, sorry. Yeah. Yeah, great. Okay, so yeah, so go back to this picture. So now that we already know, okay, how we should learn the image representations from different type of learning method, like mask modeling, like supervised learning, like contrast learning, etc. So in this talk, I will try to answer the second question, that is how we should turn the vision models to more generic, flexible, and prompt one. In other words, how we should build a general purpose vision system on top of the foundation model to address a wide range of vision tasks. So talking about the general purpose system, it's natural for us to revisit on how language models evolved in the past years. I guess we all know and hear about the GPT and the ChatGPT and amazed by ChatGPT, right? So if we take a look at the NLP domain at the very beginning, different tasks actually are coupled with different models. So at that time, actually, we can use different kind of sophisticated design architecture with maybe LSTM, maybe RN, or even CN to cope with different tasks. But gradually, thanks to the image of the transformer architecture, the building block to different NLP tasks are converging to decode-only architecture, aka GPT service, for example, GPT-3. And later on, the GPT models learned through simply predicting next token is further instructional tuned to support human AI interactions. Then ChatGPT comes, which changed not only the research community, but also the society fundamentally. So, and this only takes 4 years from 2018 to 2022. It's very short, right? So this will motivate us as a computer vision researchers to think about, so what we should do for vision. So if we do a similar projection for vision, now we are coping with different types of tasks for image level task, like image classification, image captioning, and the region level task of detection, grounding, and the pixel level task, segmentation, reference segmentation, depth estimation, etc. So actually we are curious about how we can follow a similar path like the language model to first do the unification, and second, empower a human AI interaction for computer vision model. However, we cannot easily copy-paste the technique from NLP to computer vision. As we all know, computer vision tasks actually are very diverse and fragmented, which renders several challenges to build and the so-called generative vision models. I will summarize a little bit. So first, the vision task actually need to cope with different type of input. It can be static image, it can be temporal image, it can be single modality, only just RGB pixels, it can be probably a combination of multiple modality, for example, vision and language. And second, there are different granularity of tasks. For example, we have image level tasks like classification, captioning, as I just mentioned, and also region level tasks, and even the pixel level tasks like segmentation, super resolution, etc. So moreover, the output, unlike large language model, are also of different format, containing spatial information like age, box, mask, or semantic information like class label, multi-level text, or even descriptions, or very dense descriptions, right? So all of these kind of challenges actually make it very hard for us to think about the very simple way to do the unification of different computer vision tasks. In addition to the challenge on modeling part, actually, there are also challenges on data. First, due to the different cost to enter the different type of data, by natural, we see a pyramid of scale. From the bottom to top, there are image annotations, box annotations, and mask annotations. And the semantics start from rich to poor, from bottom to top, while the granularity starts from the coarse grain to the fine grain. Second, it is much harder to collect the image data compared with the language data. So the scale of the vision data is much smaller than the language data. So this is another challenge we are facing in computer vision in terms of the data scale. So despite such kind of challenges, so as a computer vision researchers, as a community, actually we are trying to develop some kind of general purpose vision. So this is is our aspiration, right? So first, there are some efforts to turn this kind of closed set classification into open word recognition. As Sir showed in his slides, the contrast language image model like CLIP has empowered immersive zero-shot transferability for image classification. And second, we are trying to convert the specialist model to generalist model. For example, at the beginning, actually, we developed different type of models for different tasks. For example, for fast sensing for detection, mass sensing for segmentation, and a bunch of different kind of visual question answering models. But now we are seeing more and more kind of generalist model, the so-called generalist model, like pixel to sequence, like unified I/O, like XDecoder. All of these models had attempted to generalize and build some kind of generalist model to unify all of the tasks. Of course, it's just an attempt. And third, instead of merely learning visual representations, like their BIP, like Dino, like MAE, introduced by there. Actually, recently more and more people are focused on how we can build a promptable kind of system or interface beyond this kind of representation learning. So at the very beginning, actually, we are talking about, when we talk about the foundation model, we are mainly talking about the representation learning in terms of foundation. But now, actually, the times has changed. So we are more talking about, okay, whether we can train some kind of foundation model that can support end-to-end task without any fine-tuning. So this is basically the trend and the attempt in the computer vision community. And this trend, I would like to highlight the three words: open word, generalist, and interface. These three words together exhibit a great aspiration for the computer vision people towards the next generation vision understanding system. In the next, I will try to walk you through the detailed techniques behind each of their components. First one is So for the open word, we need to bridge the vision and the language. The intuition is very simple, right? The language as a common space is a common space to share information across many people, right? And the benefit of this is that, okay, we can effortlessly do the zero-shot transfer from one task to another one. And the second is the unification of different granularity. And the intuition is also very simple. So computer vision is tackling different tasks and different granularity. So we are expecting whether we can build some kind of unification model to unify different granularities to enable a cross-task synergy. For example, different tasks maybe have different kind of semantic information, have different granularity. So whether this kind of cross-task unification can help to enable some kind of cross interaction across different tasks. And for the interface, actually, we should enable the system to support and take various prompts as input. But this kind of prompt should be different from the language model. So in the vision, actually, is not necessarily a text as prompt. We can probably also draw a box. We can also draw a point, a stroke, or even a hand gesture, etc. That being said, actually, this prompt should be much more diverse compared with the language model. And the benefit is also very simple. In this way, we can reduce the ambiguity of expressing human intent. So we can use the language as a message, as a bridge to share the information. And we can also use some other type of kind of prompt to let the model understand the user's intent. For example, a stroke. So let's first delve into how we should bridge the vision and the language. So in the past years, a number of works have attempted to bridge vision and language for visual understanding at a different granularity. If you look at this two-dimensional axis, the x-axis is granularity from the image level to region level to pixel level. And the y-axis is the semantics from just a simple label, 1, 2, 3, 4, just simply a scalar label to the language labels, the semantic concept. So if you look at this figure, in the past, we have already seen a lot of effort to convert or transform this kind of regular classification task or region level classification task into this kind of recognition task. But saying that, recognition means that you need to map the visual content to the semantics, not just a discrete label. So there are two observations behind this kind of figure. So most of this method actually follow a similar kind of trend to build a bridge by converting the labels to language, because most of them probably are inspired by the clip, I would say. And the second point is that it turns out this coarse-grained knowledge can be transferred to fine-grained tasks, which has been already proved in many previous work, like the GLIP or many other kind of works in the object detection domain. So most basically, put these two paradigms side by side. You can see on the left side actually is a regular or classical image classification model. And you can see actually to classify a visual content, we just encoded the labels. So this label does not contain explicit semantics. But on the right side, actually, if I compare them, it's pretty simple and straightforward. You can see, okay, we are replacing the label embedding with some concept names, with some kind of semantic meanings, and use text encoder to encode word concepts as their language tokens. So by this way, actually, we are projecting all of the visual content, which can be described semantically to a semantic space, which is commonly shared by all of the tasks. So in the following, I will explain specifically how the reason works bridge the vision and language for pixel level task. Because in the last year, we already talked a lot about how we can bridge the vision and the language for image level task or region level task. But here I will refresh you with some kind of new works talking about the pixel level tasks. So image segmentation requires a model to group pixels with similar semantics. The task can be further categorized to generic segmentation, like semantic, instance, panoptic segmentation, or reference segmentation, given a text as input, and we want to segment specifically a region from the image, from the audio. So the methodology actually can be categorized from different aspects. First, so whether it should be initialized from clip, or we can train from scratch by combining a lot of image text pairs. Second, whether we train the model using vector supervised training or a supervised training. And third, whether we are using a two-stage model, like first a mask proposal and then a classification, or an end-to-end training. So below, I list some kind of recent work that are related to this topic. I will just pick a few of them for the interest of time. So one of the first work I would like to mention is a group VRT. So it's trying to learn to group semantic similar regions by learning from image text pairs from scratch. And it's exploit a bottom-up grouping using novel grouping block as shown here. And it will further exploit a top-down image text supervision for the visual semantic alignment as shown in the middle figure. And finally, it turns out that, okay, it works pretty well to emerge some kind of grouped region, which becomes a mask, a semantic mask for the given image. So unlike the group VRT, the mask clip actually use the clip as a teacher and attempt to extract the free label from the clip. After a bit tweak on the output layer, the model actually by itself can predict meaningful semantic mask as shown on the left side. So the original kind of clip model actually used the left side kind of attention-based pooling. I guess most of you already know that. And on the right side, actually, it's abandoned this kind of P and Q projection and directly use the value function and plus the linear layer to get the output. And finally, you can see some hidden map, which are highly overlapped and aligned with kind of semantic informations. So then, based on this kind of free supervision extraction, the user further explore this kind of pseudo label kind of mask to further train some segmentation model, which is called mask clip plus. And it turns out that this mask clip already works pretty well to extract the semantic mask from the image by only leverage the clip without any further training. But if we further train the model with some pseudo label data, actually the mask clip plus will significantly improve the performance of the semantic segmentation. So you can see here, this makes a lot of difference from the figure C and figure D. So the mask clip and the mask clip by using the user the specially designed kind of adaptation. So differ from the previous two works, OpenSig is another work, and it uses weak supervision from image text pairs and mask information from segmentation data. So by mask segmentation, mask annotation means that, okay, it does not use any label data associated with a mask. It's just use a mask to train a model to propose the mask proposals, and that's it. And based on this mask proposal, it will do very simple kind of mask-based pooling to pull the feature extracted from the clip or element vision encoder. And finally, it will do some kind of fine-grained alignment between the text tokens from the left side and the regional or mask-based pooled tokens from the right side. And it turns out that even though it's just weakly supervised by image text files, actually it will learn to segment the image very well, as you can see from this column. And afterwards, if the author further add some kind of local narration, which means that, okay, it has some kind of more fine-grained kind of alignment between the text and the image, then it will further improve performance, even though this kind of local narration developed by Google actually is still very nice, not golden annotations at all. So another mask clip, also called mask clip, and a lot of work called mask clip. And this one from UCSD actually explored supervision, supervisor training for panoramic segmentation. And it used a clip as well, but use it as initialization of the train and train the model on COCO. Similar to OpenSig, it also pre-trained a class agnostic mask proposal network and then adapt the pre-trained clip model and a new model called RAM to finally align this kind of mask code feature and the text invariance. So it turns out that we can see from this reading that, okay, the clip baseline based on this strategy does not work very bad, right? So, and after use this kind of master proposal, you can see it slightly improved the performance compared with the clip baseline, which means that, okay, so if we really want to do a very good kind of open web type segmentation, the spatial information is one side and the semantic information is another side. And based on this kind of pipeline, it will further train the model on top of the COCO panoramic segmentation data and adapt this kind of model on ADE and Pascal and to evaluate the different kind of segmentation tasks. You can see here this kind of supervised training, but in the vision semantic space will significantly improve the performance of the open web type segmentation. On the other hand, yeah, as you can see here, basically the library information significantly boost the performance, as I just mentioned. So putting all of the methods together, we can see that different methods use different pre-trained checkpoint or supervision to bridge the segmentation model with language. From the left side, actually, we can only use the image test path without any specific kind of golden supervision or master supervision. And gradually, we can initialize the model with click pre-trained model, which already contain a lot of kind of semantics, even though the semantics actually is pretty coarse-grained, but it still can significantly improve the performance of the segmentation. And then, okay, we can further add some kind of a mask to train a mask proposal network to help to extract the fine-grained region for each of the object or the background stuffs. And later on, we can add labels associated with the mask and then jointly training both the segmentation mask proposal and also the segmentation classification. And you can see here the performance, the so-called open vocabulary performance can be further improved. And finally, I did not introduce this model, but XDecoder showed that, okay, what if we combine all of this kind of data? The clip model as a pre-trained initialization and the mask plus label from the COCO or from the other supervised data set and a rich image text paths together, just put them together and jointly training on top of all of this data, it can further significantly improve the performance of the open web type segmentation. And compare group VIT with other methods. Actually, we can conclude that clip as a foundation indeed help a lot for open web type segmentation, even though the model was never trained for this kind of fine-grained pixel level alignment, but it still learned a lot of semantics alignment between the visual data and the text. And also comparing XDecoder with OpenSig and the other method, we can show that, okay, combining the image text files and the image label segmentation label data together, it can further improve the performance. So this aligns with the previous observation for region level task. If we compare with, for example, region clip and the glyph, which did not use supervised training data, which does use the kind of supervised data and the image test pairs. So that's why I have covered some recent works that bridge vision and language for segmentation. And if you go back to this picture, you will see for all of these kind of core vision tasks, the image level task, the region level task, the pixel level task, actually we have been already successfully, maybe not fully successfully, but we already built a very great connection between the old-fashioned kind of classical computer vision classification recognition model to some kind of language interface to enable some kind of fancy or powerful zero-shot or open vocabulary capacity. Although this model are unleashed to recognize open world concept, but still mostly task specific, you can see here. So at each column, we are developing some model for classification, for detection, for segmentation, but it's not necessary that we have a single model to simultaneously do all of these tasks across different granularity. This really build. So to really build the generative vision understanding model, we need to look at the task across different granularity, right? And connect them horizontally, not only the vertically. So this leads us to our next part on how to unify different granularity. And talking about different granularity, I would like to bring this figure back. But naturally, we are facing a data imbalance problem towards this goal because different kind of granularity of data actually contains different annotations. And as I mentioned before, the semantic information actually are different across different granularity. And also the spatial annotation are also at different levels. So ideally, we want to build a synergy across tasks of granularity. For example, cross-grained data should contribute to the fine-grained data or task with the rich semantics, because we can obtain a lot of image text pairs. And on the other hand, I think it's also very important if we can enable the model to share the knowledge from the fine-grained to coarse-grained to enable better grounding. So we want to build a synergy, but I'm not sure whether, okay, the following work exactly do what we want to do, but this is our final goal. So talking about this, let me have a quick recap on what kind of tasks we are usually considering, right? So image level, region level, and pixel level, I do not want to repeat it again. And in the next, I will talk about what's the most recent kind of unification methodologies. I categorize them into two types. One is output, the IO unification. So which means that it converts raw output into a sequence and develop a model to decode all of the outputs in a sequence format. And the second way is the so-called functionality unification. This kind of method actually share the comments maximally, but also with respect to the difference across different tasks. I will first talk about the high-level kind of difference again with this kind of illustrative figure. You can see here on the left side, so the output unification is trying to decode the sequence for all of the task A to Z, and use some kind of task-specific decoder to decode this sequence out to finally produce the prediction for each of the tasks. But for the functionality unification, actually, we can see that the input may be not much different, but for the output, actually, it will produce different type of output, which are shared across different tasks. And then, okay, to finally produce the output, the model will combine different output together to finally convey the predictions. So with this distinction, let's first go through some methods that unify output with sequence. Inspired by language model, most of these methods actually converts their output either spatial or kind of semantics to a sequence. So for the semantics, actually, it's pretty straightforward, right? Language model has already done that. But for the spatial output like box, mask, key point, actually, some methods have already explored a very simple and heuristic way to tokenize this kind of coordinates to a sequence. For example, X, Y, and H and W, something like that for a box. And the polygon coordinate for a mask, etc. At least some of the most recent efforts to do the unification through this kind of output kind of way. So I will also pick some kind of method and talk about it. So the first type of work I would like to mention is a Unitab and pixel to sequence v2. This model unifies text and box in the same way without any specific model designs. They both use a common vocabulary, so they convert the text to the tokens in the vocabulary, and also combine the tokens from the special output like box, like polygon, etc., to the same kind of vocabulary. And on the other hand, actually, both of these methods actually will append a prefix, a task prefix, to tell the model what kind of task the model is going to tackle at this point. For example, you can see here, so for the pixel 260v2, actually, it will append a segment and or keep on or describe this kind of task prefix to get the model to specifically decode some output sequence. And then the model will go back to check the output sequence and then use the task-specific decoder. This decoder may be trained or just a heuristic design. And when it goes to the pixel level task, actually, the previous two methods can hardly cope with this. So unified I/O is type of method that can further unify a wide range of understanding tasks, including segmentation. So to cope with this kind of pixel level or dense prediction task, the model will train the VQVE for each of the separate tasks. For example, for the mask segmentation task and for the depth estimation task, and one of these kind of tasks, the model will, the author will train some kind of task-specific VQVE. After they train the model, they can use the encoder, the VQVE encoder, to synchronize all of the input to a sequence and use encoder decoder architecture, very normal encoder decoder architecture. You can imagine it's probably T5, something like that. And to link this kind of mapping between the input sequence to the output sequence. And finally, it will decode this output sequence to some real output, like the box, like the mask, like depth, etc. This is type of method can be further used to support the pixel level or dense prediction, use a unification of the I/O manner. And on the other hand, actually, other works like Vision LM, it appeared actually last month, if I remember correctly. So this method further combine this vision encoder with some language encoder. This language encoder is different from the previous language encoder used in previous work. It's very large language model. So you can imagine could it be a llama, could it be OPT, could it be very advanced larger model. And it's plugged this larger model to help the whole system to decode the sequence. And this sequence will contain both the semantic information and the spatial information for the visual content. Indeed, it will unify a wide range of vision tasks so that the encoder decoder can be trained end-to-end for different type of tasks and different type of input and output. And also, it also, in the meanwhile, it also requires a task-specific decoder to decode the sequence to find out. For example, it will extract the coordinate and translate it into a box, or convert the polygon coordinate into a mask, etc. And also use another VQV decoder to decode the hidden features, hidden feature map, or hidden sequence to a mask or to a depth map. And it might be hard to integrate the interaction across different tasks of different granularities, because you always see a sequence. You cannot understand exactly what kind of model, what kind of behavior the model is doing. And furthermore, it may not be able to build a strong cross-task synergy as we expect. So on the other hand, some other works actually is doing this kind of functionality unification. The intuition is very simple and straightforward. The vision tasks are not fully isolated, right? So for example, a lot of tasks share the box output. The generic offset object detection, the phrase grounding, the regional caption, it's needed to predict some kind of box. And then this can be shared across different tasks. And the mask output can be also shared by instance, semantic, panoptic segmentation. All of these type of segmentation tasks actually can use a single mask decoder head to decode the mask. And also, of course, the reference segmentation, the example-based segmentation, etc. And for the semantic output, actually, it can be shared across different tasks like classification, image captioning, regional captioning, detection, segmentation, a lot of different tasks. That being said, okay, so what if we what if we unify this kind of different tasks based on the categorization of the output? So you can imagine, you can see there are high-level two types of output. The first output is a special output. So either the box or the mask. And also the second type of output is a semantic output. Is just described by, for example, through the language. So you can imagine, okay, what of these methods actually are trying to follow this kind of abstraction and unification in terms of the functionality. So I will also pick one or two to mention. So the first one is the Uniperson V2, and it's trying to unify classification, architecture, instance segmentation, image text retrieval, image captioning. Yeah, you can name it. A lot of different tasks, and basically it's exploit a unified decoder G, and this G will take different type of queries. It can be the queries from the detector for the detection. It can be the queries from maybe the segmentation or the captioning. So basically, you can imagine, so if we can build a unified decoder, and then this unified decoder can take different type of queries as input and decode a different type of output. And you can combine the output together to finally support different type of end tasks. And likewise, I would like to also mention the X decoder, the generalized decoding for pixel, image, and language. So this work is also exploiting a single unified encoder decoder architecture, which is called X decoder. And it takes two types of input, the latent queries and the text query. And it will produce two types of output, the semantic output and the spatial or pixel level output. And you can imagine by composing different type of input and output, it can support different tasks. And for all of these tasks, actually the model does not have separate kind of parameters. The parameters are fully shared across different tasks. It's just a routing for different tasks. Yeah. And based on this, for example, for the segmentation or for the generic segmentation, if we do, in this case, we do not have the text encoder, then we just use a latent query to ask the model to decode the mask for the whole image. And for the reference segmentation, then we feed some text embedding from text encoder to the X decoder, and then it will automatically understand what's the condition and then specifically segment the object. Likewise, for the image text retrieval, we do not need to produce a pixel level output. We just produce the semantic output and compare the similarity scores between the semantic output and the text embeddings. And finally, we can further do the image captioning and visual process answering by producing the output from the right side of the X decoder. Even though, okay, there is no other changes, it's just the selecting which part of the output to predict to make the predictions. So by saying this, actually, I briefly cover so how we unify the different granularity of tasks in the autonomous stage. So it can be categorized in two different ways. The first is the I/O or output unification, and the second way is a functionality-based unification. And based on thus far, you can see, okay, we are doing some kind of unification, and also we are doing some kind of effort to trying to build a generalist model, which can generalize to new domains in terms of the vocabulary, in terms of the concept, and also it can be generalized to different types of tasks at a different granularity. So we are drawing these arrows vertically and horizontally. So it finally can cover different tasks in the computer vision. And by saying this, actually, I would like to also mention, okay, so there is also another workshop called Computer Vision in the Wild. It's happening now, and if you are interested to know more about the effort towards next generation general purpose computer vision for classification, detection, segmentation, and beyond, yeah, please stop by this afternoon after you finish this tutorial. Yeah, and so the next part is about the promptable interface. So I will briefly walk you through the recent effort towards generalist vision and in terms of how we can build a promptable interface. So this actually is inspired and recently developed by inspired by the ChatGPT and recently developed by several teams. So the motivation is pretty simple: how we can enable vision models to chat. So you can imagine, if we only have the GPT, maybe it cannot be easily directly used to finish the daily task we have, for example, coding, writing an email, etc. But if we can do some kind of instruction following tuning and human feedback in the loop, etc., we can finally build some kind of conversational AI like the ChatGPT developed by OpenAI. Likewise, given that we already have a generation model, in the last slides we already draw the arrows vertically and horizontally. We already cover all of the tasks. Let's imagine, this generative vision model is perfect. Then what we can do to enable a good kind of interaction between the human and AI model. So in this, at this point, actually, we probably have two kind of ongoing efforts in the computer vision community. One is that, how we can develop a prompt-able interface for in-context learning, because this is indeed a very, very good property and the functionality showcased in the larger model. And the second part is that, how enable an interactive, multi-round interactive between the computer vision model and the human, so that it can help the human to finish complicated tasks and gradually refine the prediction results. So these two aspects actually have been recently explored to some extent. Of course, there are a lot of kind of open space. I will just briefly go through two works. For the first part, the in-context learning for vision. So this work is from Berkeley, and it's called visual prompting while image implanting. It can candidate the in-context sample. You can see the first two. The task import example, just a regular RGB image, and then it will have the mask, and ask the model to predict a new mask for the query at the state column. And somehow, actually, the model works to some extent. And of course, it's not that good compared with segmentation model I showed earlier. For example, the OpenSig, the XDecoder, fireware, I would say, But this is a good effort to pursue this kind of in-context learning for computer vision. And another work is called CVPR. Actually, it's appeared maybe 2 months ago. This is share a very similar spirit to the previous work. Given this kind of input image example, and also the model take a mask of that image and then give a new image. For example, give a new image like this, and then it will predict the mask for the Liberty statue's face. So this is basically pretty simple and straightforward, and it looks like we are somehow actually achieving the in-context learning for like the larger model, but I would say it's still far away because it's only cope with this kind of specific task like segmentation. But it's a good attempt. So beyond this kind of prompt-able interface for in-context learning, I'm sure you guys are very familiar with this work. It's enable an interactive interface for vision, which means that the model can support a multi-round of interaction between the human and the system. So this prompt segmentation can take different type of interaction mode. As I mentioned before, the computer vision task is different from the language model or language task in that it does not only take the language as input. It only takes some other kind of special interactions. For example, the point, the bounding box, and the stroke, the mask, etc. This kind of prompt is also very expressive to convey the information to the system. So you can imagine in the future, we probably have a VR glass, and then it requires some kind of maybe interaction beyond the language as well. And based on this kind of promptable interface, they develop some very simple, straightforward encoder-decoder architecture. And based on this encoder-decoder architecture, it has run some kind of flywheel of the data to collect a lot of data. 11 million of images contain maybe over 1 billion masks, even though one of the masks are automatically annotated by the model. And finally, it trains some model to enable this kind of interactive segmentation. And this interactive segmentation are mainly achieved by deliver or feed the previous mask to this block, and then use a convolution network to encode the history mask, and finally gradually refine the mask given some kind of prompt or box-based prompt. And for SAM, actually, it's already has been widely used in different computer vision tasks. In this sense, actually, it can be called the foundation. So based on this kind of end-to-end segmentation model foundation, so a lot of people have explored different applications. For example, combine the segmentation model with implanting to fill the mask region, or use a segmentation model to help to track the video object in a long video sequence. And then it can be further applied to the medical images across different types of tasks, including the segmentation and the detection. And again, so this kind of SAM is very powerful in terms of the promptable interaction. But as I mentioned, this SAM model actually only supports the spatial interaction. Prompt, box, it does not show a very, very good kind of capacity for the language or semantic prompting capacity. SIM is another work. It's called segmentation everything, everywhere, all at once. And the reason why it's called like this is because, so the everything means the model can predict all of the labels, name all of the entities in the images. And everywhere means that, it can predict every pixel into a segmentation mask. Or advanced means that, it can combine different kind of prompts together by adding, for example, visual prompt plus text prompt, or reference prompt plus the text prompt or audio prompt, etc. So finally, you can imagine this model can do a very wide range of segmentation tasks, can support different type of prompting methodology or format. And it also supports a very good kind of interaction. So you can see there are some kind of examples. I will not explain it one by one. I just want to show, this is one of the example. Let's say we just draw a stroke, just a simple stroke on the first image. Then the model will use this as a reference prompt to segment all of the specifically specified object in the consequent frames. And even though there are a lot of kind of deformations, you can see here the flies from this image and to this image, and also zooming and blurring, etc. So this is pretty straightforward for you to use in a zero-shot manner, even though it's never trained to accomplish this task. So finally, I would like to have a quick recap on what I just discussed. So in this talk, I'm mainly talking about how we can achieve a very good kind of promptable and flexible and generic vision system interface. So it's more like an interface, it's not just a model. So to achieve this, so we first want to bridge the vision and language. I would say for this part, in the last 2 or 3 years since the clip, actually a lot of effort has been spent on this domain, and it has been successfully reshaped the researchers, computer vision researchers for classification, for detection, and for segmentation. Now we are not distinguish the vision language and the vision task anymore. And on the second point, we want to unify different granularities. So the different granularities, if we can unify different granularities, so the final goal is that whether, we can build a very good synergy across different tasks, because we do not want to unify this task for fun. So we want to build a coherent and a kind of a flexible system to support different tasks. And finally, it should take various prompts. And I would like to highlight here, for computer vision tasks, the prompt should not be only language prompt. It should be also contain some kind of special prompt so that it can be complementary to each other. And finally, convey the intent. So to the end, I would like to share this work conducted by our MS colleagues. And this work actually claimed that, they found some kind of sparks of AGI in the GPT-4. And indeed, there are some kind of sparks. So in the bottom, actually, you can see here, the model, even though without any kind of visual learning, can gradually learn to how to draw this kind of unicorn based on the tool called Tixi. And you can imagine, so how capable it can do. And it was impressive to me as a computer vision researcher. But So talking about AGI, I want to show you this figure. But natural human brain has a lot of neurons which are responsible for different functionality and cooperate with each other to finish the complex task. It involves language, but not only language. It also involves the vision, the auditory sensation like speech, like audio, and also motor control. So in this sense, if we go back to our computer vision community, so it still have a long way to go, right? So we are trying to draw some dots between the loop, between the individual computer vision task and the unified generates the model, and then further, build the connection between the unified model to the finally interactive and the promptable kind of interface. So you can see there are a lot of works are trying to pursue that, but it's still far away from the final goal we are imagining. So that's good, or that's bad, but also good because we are fortunate. All of us are fortunate to have a lot of kind of imagination to pursue this kind of generous model for computer vision. So finally, I would like to mention that, what we can do with this kind of generous vision understanding model. So we can use it to enable a intimate cooperation with large model for physical world tasks. And finally, we want to give large model a very kind of precise eye. It's not just a broadly or coarse-grained eye. It should be a precise eye. And also we can further combine it with some kind of image or video generation or editing task, as well described by the next speakers. And so finally, so we want to achieve this kind of multi-sensory general intelligence that can see, talk, and act in both the digital world and the physical world. So this is basically a very, very great aspiration. But right now, actually, as a computer vision researcher, actually, we have a lot of space to explore towards this kind of generous computer vision model for understanding. So that's it. So thanks for your attention. Oh, I'm sure.
我说光点可能以前呢，我在收拾的范围。
或者你直接取它的距。
Okay, yeah. Okay, so yeah, again, thank you everyone for coming to our tutorial. Next, I will be talking about the text-to-image generation and how do we actually produce visual data. So still starting from these previous figures, previously the previous speakers have talked about the bottom left center about how can we consume visual data to train vision understanding models that can have good image representation as well as building more universal image understanding model. Next, we will try to touch a little bit on the inverse direction on seeing how can we go the inverse direction and produce visual data. Specifically in this tutorial session, we'll be focusing on the so-called alignment perspective in producing the visual data, that how can we get data that actually align with the human intent so that we can make such data actually useful. So starting from the basics of text-to-image generation tries to generate high fidelity image condition on the text input. So this is a special problem under the conditional image generation that tries to not only generate high quality image, but also wish it to be semantically related to the input condition, where in this specific case to be the text description of the image that we try to have. So instead of trying to give a comprehensive overview of all aspects in the text-to-image generation, which as we overviewed in the bottom figure is evolving very fast. So in today's section, where we try to introduce the text to image from the so-called alignment perspective about how can we have models that better aligns with the human intent, or in another word, how can we have the systems more easily help users generate the exact visual contents that they are imagined, or just to have the text to image easier to use. So zooming into this broader motivation of having the more aligned text to image generation model, specifically we'll be introducing related works mainly from the following 4 aspects. Starting from the controllable generation, that in addition to the image description, that is the text part used in most text to image generation, in some scenarios, we might be interested in having additional input conditions or input channels that the users can use in order to make the generation easier, or helping them more easily convey what they actually intend to draw. And next is the editing part. So editing is also a very important channel in the alignment, that in some scenarios, we might be mostly happy about the image we generated or already have, except we might want to tweak a little bit. For example, it can be either the image style, we wanted to change the style a little bit, or spatially only at a specific location, we want to add or edit an object. So in this way, editing provides us a tool to keep the majority of the image, but only to modify it a little bit to perfectly align with what we actually want to generate. Next, we'll talk about better following text prompts. So although text-to-image models are trained with the hope that it can generate an image that is semantically related to the input text prompt, as we will show later, unfortunately, this is not always the case, that sometimes, especially when the text description becomes more complicated, the model might just decide to overlook a certain objects or get confused with some detailed attribute description. For example, apply the color onto the wrong objects. So there has been also a line of research exploring how to have the model more strictly following the input text prompts, and in this way, provide a way for people to more easily generate the exact image they are thinking about. And finally, is the concept customization, that sometimes we may wish to have the model to have some visual content we already have, for example, our own pet dog or a specific cartoon characters that is just designed by ourselves previously, and apply these visual entities onto different scenarios. So those visual entities might be difficult to specify by the natural language. For example, how exactly our pet dog should look like, and differentiates them with all the remaining dogs. And instead, it might make more sense to have the model take such additional concept and somehow customize an open-ended general T2I model into our specific use cases. So these are some interesting alignment-related generation topics that we wish to cover today. Before diving into all of those exciting works in all those sub-directions, maybe let's first have a quick overview of some basics in the text-to-image generation. Again, text-to-image generation is a conditional generation problem that takes text as the input condition and tries to produce an image that is both of good visual quality and meanwhile semantically corresponding to the input text prompts. This is usually done by using the paired image text data, where the text part in this image text pair is used as the input to the system, and the corresponding text in the pair is used as the training objective. So by training the model to actually mimic or reproduce this image, it not only enforces the model learn to generate reasonable images, but also because the image text is paired in the training samples, it implicitly learns to generate image that is semantically corresponded to the text input. So zooming into the image generation part, here are several representative image generation techniques. Starting from the classic generative adversarial network, or GAN. So GAN consists of a paired generator and a discriminator. So generator tries to generate an image from noise conditioned on the text input, which competes against the discriminator that tries to distinguish whether the input image is real or fake. And by having these two counterparts compete with each other, generator learns to produce more realistic image, where now the realistic is actually defined by whether this discriminator can actually distinguish whether it's fake or real or fake. Next, onto the more recent approach, one representative is the autoregressive transformer-based approach. So such method will usually take a paired image tokenizer and a detokenizer with the core idea of converting the image first into multiple patches and mapping each patch into a discrete index, where this index indicating the refers to the index of a specific token in the codebook of the image tokenizer. And then with this paired tokenizer and detokenizer, for example, a VQ-GAN, we can project an image prediction into a set of discrete tokens still arranged as a 2D matrix. Sorry. And after discretize the image prediction, we can then have the model predict tokens one by one following a specific order. For example, usually starting from the first row from left to left, then the second row, so on and so forth, and we can complete the entire image. And then with this predicted set of discrete tokens, it can be sent back to the detokenizer part to recover the final image we try to generate. And instead of predicting those discrete tokens one by one in an autoregressive way, there are also some very interesting work showing that we can have certain scheduling policy that we, at each step, we generate multiple tokens jointly, so that instead of having to reproduce a quite long steps, we can greatly speed up the inference process by generating multiple tokens at the single step. And finally is the diffusion. So diffusion involves random noise into the image as a multi-step denoising process. So the goal in each step is to predict a meaningful, semantically meaningful noise to subtract from the initially randomly initialized noise, so that finally we can end up with an image that is both of good visual quality and semantically related to the text input. So next, we will use one specific model, the stable diffusion, as a closer look example to help us better understand some like what a text-to-image model might look like. So here we choose stable diffusion for several reasons. The first is that this is one of the very popular open source model, and as we'll show later, many of the alignments work we are going to introduce later today are actually built based on this model. And also, it represents one of the diffusion-based generation method. And finally, how the text actually operate on the image, which is one core problem in text-to-image generation. The cross-attention mechanism are actually also shared by many other non-diffusion-based methods, for example, in the autoregressive generation. So we think this might be a good example to help us better understand how a typical text-to-image generation model looks like. So let's start with the stable diffusion's architecture overview, or short for SD. So as shown in the right side, the architecture mainly consists of three parts. So in the leftmost is a pair of variational autoencoder, or VAEs encoder and decoder, which as shown in the top right can take an image and project it into a latent, which the diffusion process actually later operate on. And also take this latent and use the paired decoder to recover the final image, or the original reconstructed image. And the second part is on the rightmost side, that is the conditional encoder. So if specifically when we are talking about text-to-image generation, that we take text as input, this conditional encoder can be a clip text encoder that takes a language sentence as input and produce a set of word embeddings. For example, a typical magic number is 77, which is the maximum length of the clip text encoder. So each word will have a text feature encoding, feature, which are then sent into the standard part, which is a core part of the model, the conditional text condition denoting unit. So the process might be more clear if we have a closer look at the right side inference flow, that assuming we have the model already being trained, how can we, so in the inference time, what does the the latent flow look like, so that we can end up with a good looking image? So starting from the top side of the right side image is the input to the system, which basically consists of visual and text part. So the text is on the right side, which is a sentence input, which is then fed through the frozen text clip text encoder and producing a set of text features. For example, a typical dimension is 77, which is the maximum number of word tokens, times a text embedding length, for example, 768. And then in the center is the visual related information or the latent, because the stable diffusion actually operates on the latent space. So this latent contains the visually related information. Basically, this is where we store the image information that we try to generate. So as mentioned later, this latent actually starts with a random noise, and then this visual and text information are sent into the center, the largest block, which is the text condition, the latent unit. And the goal of this model is that we try to train it to predict a meaningful noise to subtract from the previous latent, such that the output of this unit in each round will be sort of a less noisy version of the latent. And this process is done repetitively for multiple times, as visualized in the bottom, the gradually denoising process, so that in the final round, hopefully we can end up with a good latent that we later send through the decoder of the VAE that hopefully can give us a good looking image that is also semantically related to the text input. And as we might see, actually the core magic or the core part is mostly in this center text condition unit, that how does the framework actually look like, so that it can predict meaningful noise to subtract, which finally ends up with a meaningful image that we want to produce. So here we also further zoom into this text condition unit on seeing how the text condition actually operates on the image feature or the latent, so that we can produce a reasonable image. So at a high level, this is a unit. So at the bottom left side, we just show some very abstracted view of basically what the unit look like, which consists of a series of downsampling block as well as later upsampling block with some skip connections in between. Zooming into any of these specific blocks. So here we show a downsampling block, which is also the same for an upsampling block. So each of these blocks take both the latent, basically the visual information, the text information, as well as the T. T indicates the denoising timestamp, telling the model like basically how noisy the input latents might be as input, and feed through this block and try to produce the next steps of latent. So inside this block, there are mainly two operations. One is the image text cross attention. The other is the convolutional downsampling or upsampling layer. And further zooming into this image text cross attention, this is basically actually where the text and the visual features see each other. So if we're looking into that, this is basically a quite standard cross attention, where the query is the visual related information, basically this latent, except we add some like time step related information. And the key and value would be the text word embedding. So again, the 77 refers to the maximum length of the text sequence. And basically we'll do the attention mechanism. And as we can see, by simply computing the attention maps by producing the query and key, we will end up with an image text attention map that shares the size of the spatial dimension, height times width, times the number of text tokens. Or in another word, during this cross attention process, each word in the input text prompt will attend to spatially to the latent, so that each word will attend to different parts of the latent. So this is basically one core part that how this generation process or how text actually will later influence the generation process. So actually we highlight this attention map because, as we will see later, many of the alignment work are actually trying to manipulate these attention maps. So I thought it might be helpful to talk into a little bit more details on this cross attention mechanism. And again, in addition to the diffusion-based or stable diffusion, this cross attention is also shared by many non-diffusion based methods on how to generate image condition on the text. So I have just talked about some very brief overview of the basics in text-to-image generation. And next we could continue on to the following four aspects that we talk about in the so-called aligning human intention in text-to-image generation. Again, controllable generation, editing, better following prompts, and the concept customization. We start with the controllable generation. So the overall motivation is that the text in a typical text to image generation refers to the global description of the entire image. And in some case, it might be helpful to combine such global text description with some other format of optional additional input conditions. For example, either the layout leading to the grounded text description or some other dense controls, for example, mask, edge maps, scribbles, and so on, so that the users can more easily specify the, for example, layout and other aspects of the image if they desire. And by the way, for the later other aspects, I will also just list the related papers on the right side, which due to the limit of time, we might only be able to sample a select of them to give a rough idea about how each of these sub-bullet points are talking about. So next, we will continue with the first part, that combining text with the layout. Again, we start with the motivation. So the text in text-to-image generation, as shown in the bottom left, usually refers to the global image description. For example, for the leftmost image, it can be a description like a dog sitting next to a water bowl. So in one of these recent work record, the authors try to explore if they can expand the sort of definition of text from the text only, basically containing only text word, into a mix of the so-called grounded global and region description, with the major motivation of seeing if we can have text only describing a specific part of the image. For example, we can specify in the bottom left corner of the image, we want to draw a silver bowl with water in it without having the text description influence any part of the other part of the image. So method-wise, such expansion is mostly done on expanding the input sequence vocabulary. So basically including additional box tokens in addition to the text tokens. And as we might see in some of the previous image understanding work, we have also discussed how to expand the box vocabulary, except now it is used as the input side and also show that they can also providing a more easy way to provide the grounded description where the added box tokens serve as a spatial modifier that only operates on the text to follow it. For example, we can specify in a certain region what this player's appearance and other detailed features that we try to have the model to generate. And the model actually also built based on Stable Diffusion is then fine-tuned to understand the meaning of such box tokens, so that on the input side, user can generate the mix of such box and text tokens to provide the grounded referring. And other than do such expansion or the grounded control on the input side, another effective way is to expand it with the grounding tokens. So let's first talk about what might these grounding tokens, what information might it contain. So it is actually a mix of two parts of information. One is the grounded text entity, for example, the text word like the wedding cake, and it also combines the feature with the spatial coordinates, for example, the bounding box coordinates, so that the final grounding tokens contains the information of both some part of the grounded text referring, as well as the location of which part of the image this text referring should operate on. And then the study, the Gleason study introduced the new gated self-attention layer, which is inserted into every transformer block inside a pre-trained text-to-image models. So this added gated self-attention layers is added to help model understand the meaning of these grounding tokens, or in another way, using such grounding tokens to provide the spatial controllability. So one code design is shown here, basically the gamma hyperparameter, which is zero initialized. So this is quite important as it as during the fine-tuning stage, it enforces that this additional added gated attention at the very beginning does not influence or worsen the original pre-trained text-to-image generation, and it only comes to place gradually during the model fine-tuning so that it can keep the original text-to-image generation capability, but also provide our desired additional channel of the grounding or the layout controls. And as shown by the authors, such method can effectively enable a wide range of such grounded controls. For example, combining text description with the bounding box grounding, key point grounding, and other types of spatially aligned dense conditions. And in addition to box or layout, people are also interested in seeing if we can further include other types of sort of dense control. So here by saying dense control, we mean that the conditions that is usually represented as a 2D matrix more similar to the image. Examples could be the segmentation maps, the depth maps, normal maps, and so on. So one representative works along this line is the control net with the architecture shown on the right side. So the core idea is to copy the encoder part of the pre-trained stable diffusion as an additional conditional branch, which also takes the additional condition as input. And only this additional added conditional branch is fine-tuned so that it can understand this additional condition input. And also it's quite important that the output of this added branch is then sent back to the decoder branch of the main framework after this specially designed zero convolution, with a similar motivation that in the very beginning, the fine-tuning does not look at any information on this additional condition branch. Instead, it's just sort of a basic text to image as in the stable diffusion pre-training. And later, when the model learns to set these zero initialized parameters to be non-zero, this additional branch of condition gradually coming in and achieve our goal of the combination of text and other dense conditions. And also along this line, further extended from control net, recently there are also some very interesting work on building a more unified solution for control net. For example, they try to see if we can build a single model or more precisely a single additional branch that can operate different type of conditions. And on the one side, such unified model allows a single model that can now take different types of conditions. And also it's interesting that they can now take the composition of multiple different types of conditions. For example, we can now take both the human key post map as well as the segmentation map as two conditions in addition to text and generate the corresponding image. So all previously introduced method that would actually require certain extent of model fine-tuning, either the entire framework or specific adapter-like layers. And other than the fine-tuning, there has also been some very interesting recent work on seeing if we can have such additional guidance, but only in the inference time. So so the universal guidance for diffusion model is one representative work, where the core idea is to extend the idea in classifier guidance to expand the classifier in the classifier guidance into the general guidance general discriminator guidance. So here, let's take detection as an example, where specifically for the detection case, this letter F indicates a detector, for example, fast SNN, which operates on the intermediately generated noisy image Z0, and it will compute a loss with a ground truth label C. So this here by saying ground truth label, basically it means the exact layouts that we try to guide the model to generate. And finally, it will compute some object detection loss indicated by letter L, where this numeric value is used to guide the intermediate generation process so that the generated image would better follow the input boxes, for example, shown in the right side image. Although as we may see, it didn't follow that strictly compared with some of the previous fine-tuned method, it's still quite interesting that we can being able to achieve such inference time guidance without explicitly requiring the model to do fine-tuning. So previously we talked about controllable generation, and next we'll talk about the editing or image editing. So editing is also another important channel in the alignment in T2I generation, with, again, the motivation being in many scenarios, we might have an image that are reasonably good, but we want to change a specific part to make it a perfect line with what we intend to generate. So editing contains very different aspects. For example, the image content we try to edit, for example, spatially for a specific region or the global image style, as well as how we specify the editing instruction. For example, describing the final image we want to have, describe the object's region we try to edit, or just the instruction like style. For example, make the image look a different style. So next, we will sample several representative work, try to give a brief overview of some representative works in editing. Yeah, please. Starting from, Starting from the first is the spatial blend, which is the latent. So assuming we have already know the region to edit, we can apply a spatial map that only operates on this specific region, and we can just blend the latent where the foreground is generated by our input text and the background it just keep the original image, so that by spatially blending them with the given mask, we are able to generate the new edit image, just simply editing the content inside this mask region. However, having a mask is sort of a strong assumption, as it might be difficult for users to generate, and the model generated masks are not always that reliable. And also the edge in this hard blind of the foreground and background might have some generation artifacts. So some other study also show that specifically for the generated image that we try to edit, one effective way might be just to directly manipulate the image text cross attention map. As we mentioned later, this cross attention map would implicitly have some spatial attended patterns, so that it can achieve certain editing operation, for example, word swap, adding new phrases, and attention reweighting. Or more specifically, it will maintain two sets of cross attention maps. So one is for the original image, so basically show for this square-shaped lemon cake that is the image we previously generated. We might want to keep the overall visual looking of this image, but try to just make it more monstery, than basically a monster cake. So if we just use this new prompt of monster cake to generate the image with the cross attention map empty star, it will be a reasonable image, but it will basically visually looks very different from the original image that we try to edit. So this study showed that we can simply have a clever way to combine this empty and empty star into the new set of attention maps indicated by this empty head, and just do the generation with this new empty head, so that we can end up with this image show indicated by the goal on the right side, that it both keep the overall visual looking of the original image, but also adding the new contents we try to edit, basically some monster related visual properties. And again, here are just some more visualization of the supported word swap, adding new phrase, and attention reweighting operations. However, being able to only edit the model generated image might be sometimes more restrictive. So there are also studies try to see if we can have editing on the natural image for any photos, for example, our own pet dog, whether we can make it sit, jumping, or doing some other actions. So the core idea of this paper is starting from the original image. So basically the image we have, like the bird standing, whether we can find a corresponding text embedding that are likely being able to reproduce or regenerate this image if we send it through a generation model. So after optimizing that, we'll have the original text, and the text we try to edit, basically the description, like we want to have a photo of the bird spreading head, but spreading wings, but still the same bird. So after finding this optimized embedding, or basically the semantic related to the original image's text embedding, we can simply interpret them or combining them to produce the final image with the same bird, but wings spread. So although like having method to obtain such original text shows a way to achieve some level of natural image understanding, obtaining such original text is not always easy, and as shown in the previous study, it only works well when we fine-tune the model for several steps, which might be a little bit complicated. So intuitively, it might make more sense if the model can understand so-called instruction text. For example, instead of saying the description that we want to have a bird spreading wings, we can just say we want to have the image, but with the bird have wings spreaded. So basically, the problem is that if we can have pairs of image data, as shown in the right side, as well as the corresponding instruct text, we can simply train an image text condition, an image-to-image model that can do such editing or such appearance changes. However, the problem is that previously there does not exist the data. So in this paper, the authors show that they can use starting from one sentence and use the large language model to generate, one is the edited caption. So basically starting from bird standing into bird spreading wings, as well as its corresponding instruction, basically having wings spread. And then sending all these two sentences One is using the Stable Diffusion to convert bird standing into an image. And also we previously mentioned there are some methods that we can edit the generated image, for example, prompt to prompt, and we can use the generated image as well as the paired edited caption to get a pair of samples, basically the bird is standing and bird spreading wings, as well as the corresponding text instruction, so that we can train a image-to-image model that can understand the instruction style text editing instructions. And finally, in the editing thread of work, instead of developing single models, there has also been a recent trend of building effective editing system based on the external modules. So here so one effective is to combine it with some strong segmentation model. For example, the SAM and SEAMs we previously discussed, so that by seeing a natural language description, the model will automatically find the region to edit as a mask and change the visual appearance in that region accordingly. And also another trend is using the large language model as the center to training different tools so that it can know what the editing operation it should do. So in the final part of today's scenario, we will zoom into such multimodal training and talk more about such systems. And we'll talk about controllable generation and editing. Next is better following text prompts. Although we train the model with the hope that it can generate image semantically corresponding to the text condition, in many scenarios, unfortunately, this might not be the case. So there has also been work in trying to explore if we can simply have the model better following text prompts. So one thread of work is doing the text time guidance. Again, the problem is that when the query becomes more complicated, it might have the following problem. For example, the attribute leakage. Instead of generating a red car and a white sheep, it might just decide to generate a red car and a red sheep instead of a white one. And also other problems like interchanged attributes and missing objects are also commonly appear problems in not strictly following text prompts. So one way, as shown in this work, is simply to manipulate the value in the image text process attention based on the linguistic parsing tree structures to enforce the model to evenly looking at all the parsed noun phrases instead of looking at all words equally, but just to parse out all the noun phrases, for example, shown in here, and enforce the model to assign equal weights when doing the cross attention, so that it learns to look at all the noun phrases appeared in the image. With a similar motivation, there is another work showing that instead of doing such redistribution in the latent space, it might also be effective to adding certain related localization directly on the attention map, with the core idea still being trying to enhance the maximum attention for the most neglected subject tokens, which later derived into this loss that the maximum attention map for any words should be close to 1, that for any words, it should at least attend to one spatial location, which hopefully it will later draw these noun phrases there. So again, by adding this additional latent and additional loss and use it to guide the latent, the author also show that it can generate the noun phrases or the text prompts more correctly. And other than the test time inference, there is also a line of research tries to do additional stage of fine-tuning that tries to have the model directly out of box, more strictly following the text prompts. So partly inspired by the success of IL human feedback in the large language model, there has also been works in seeing if we can use reinforcement learning to optimize diffusion models to perform better following different downstream objectives, where one of them could be the prompt alignment. So specifically, this prompt alignment could be we use a large multimodal model, for example, the representative lava, to take the generated image and generate a description of what is there in this generated image, and compute the text similarity with the input prompt, which yields a score basically indicating the semantic correspondence between the generated image and the input text prompt. And this score is used as a reward to optimize the original text image generation model. And as we can see in the right side figure, where the x-axis is the number of additional policy update steps. So we can see that by tuning the model for additional step, the similarity score actually goes up, which is also indicated in the centered visualization on different text prompts. And finally is the concept customization that sometimes we might want to add additional visual concepts into our generated images, for example, our own pet dog. Again, the problem setting is having several images, for example, 3 to 5 images that we try to generate, but with it of different actions, with different styles, and combine it with other different things. So this line of work starts with customizing one single concept based on several images, and with the pioneer work being text inversion, dream boost, and other related works. So the key idea is to add an additional unique identifier V token into the input vocabulary that the model is fine-tuned to understand. This V token basically means our own specific pet dog instead of any general dogs. And the model is then fine-tuned to understand the meaning of V, where specifically in Dream Boost, one problem they mentioned is that if we can jointly fine-tune the entire framework, it will perform better, with the problem being it might forget what the original or general dog might look like. So they propose to generate several samples for the dog and jointly train it with the reconstruction loss to learn our own dog and the prior preservation loss to remember what the original dog looked like, which have been proved to be quite effective. And also further extended, there are studies showing whether we can learn multiple concepts instead of a single visual concept, where this multiple concept can also be either coming from multiple set of images or an image with a mask indicating different visual entities inside of it. And finally, so the previously introduced method would require the test time fine-tuning, meaning that if we want to add our own pet dogs concept into the stable diffusion, we would need to fine-tune the model by ourselves, which might be inconvenient for the users. So there has also been some interesting work in using the idea of retrieval augmented or in-context generation that at the test time take additional image as condition and tries to achieve the similar goal of concept customization. So finally, as a quick summary in today's presentation, we talk about the following 4 aspects of related work in the alignments in text-to-image generation, starting from controllable generation, editing, better following text prompts, and concept customization. I would like to quickly end up with some interesting discussion, or it's more like an observation. So one is the discussion in the text-to-image generation community regarding the open source versus closed source code bases. So as we observed, there has been quite powerful model in both directions, where the open source community usually would have a more faster support for those kind of additional controlling method as well as those new functions. However, we have to admit that for the closed source models, it might work well for especially certain challenging cases, for example, face generation. We're not that sure why, likely due to the specific or better data quality, but we hope that in the future, these two parts could sort of inspire each other and generating even better text-to-image generation models. And the second is about the so-called consuming and producing visual data, which is related to the bigger scope of this today's tutorial. So such closed loop can be done at different levels, for example, data model training objective. But now if we just simply look at the so-called data loop, basically the understanding model, image to text, and the generation model, text to image, has already shown a quite promising loop in generating data to help each other. For example, many of the generation model we introduced today are already using understanding model, for example, image caption, to produce pseudo data to help the training. And for the inverse direction, recently there has also been some great advancement in using synthesized data to help analysis tasks, which is effective in the few shot setting and in the setting where the data is not that easy to acquire. And in the future, I think this is a very exciting topic of how this synthesized data, to what extent could help the general understanding models. And we're excited to see the future works along this direction. With that being said, that's the end of my presentation. Thank you.
Hello, everyone. Hello, everyone. My name is Chuan Li. Today I'll be talking about large multi-model models, or LMM. You all know that ChatGPT or multi-model GPT-4 is quite popular nowadays. And today I'll try to help to build a minimal version of multi-model GPT-4. And I think this might be an interesting topic nowadays. For the rest of the tutorial, Linjie and me will cover different ways to leverage large language model, or LLM for multimodality. I'll focus on the end-to-end trained models, and so that we can make large language models see the image and understand and reasoning over it. This is today's agenda. There will be 3 parts. First, I'll talk about the background, covering the large multi-model models, and most importantly, multi-model GPT-4. And then moving to the second part, to prepare ourselves on the necessary background knowledge, I'll talk about instruction tuning for language models. In the last part, I'll talk about how we do instruction tuning in the multi-model space. As a running example, I'll mainly talk about Lava and how we build the data of Lava, how we train the model. And then based on this, we see that this is a quite hot topic nowadays. Summarize the papers proposed in the past 3 months and trying to give you some insights. Okay, let's start with the first part. The existing large models in the multi-model space. I think most of the models, they share the two things. One is a model architecture. The other one is a training objective. In terms of the model architecture, I think there are 3 parts, including the vision encoder, the language model, and optionally, we may build some trainable collection modules to connect the vision part and the language part. In the end of the day, what these models are doing is to input the image and trying to decode it or convert the image into a text sequence. In terms of training objectives, most of the models share the same training objective, which is autoregressive loss on the language output. And in terms of because all the models are built based on transformers, and in terms of the attention map in the transformers, they are using the cross attention image to text cross attended image to text generation map, meaning that all the image tokens attend to each other. And for the text part, and the predict text token will condition all the image tokens, and the previous text tokens. Oh, by the way, I'll share the slides deck later in our website, so that you can get to revisit the full material later. So we have covered the training objective and the architectures. So now let's use some examples how existing work actually implement those 2 things. And so as a first example, the models trained with image test pairs. We are using 2 existing models. One is GIT, the other one is Belief 2. And we see that they all have the 3 modules in terms of architecture. So for GIT, it is based on the image encoder is based on the contrastive train of Lawrence model, and they initialize the weights from there. And they also build a language model from scratch on top of the visual features, and they train the model end to end. And on the other hand, Believe 2 was proposed early this year, and they keep the language model, they keep the pre-trained vision encoder and the language model weights frozen, and they add the lightweight module called Q-former, and it turns out this bootstrapping approach is quite sample efficient in terms of training samples. As a second example, so we also see a flamingo model. This is the multi-model models that are trained on the interleave image text data. Similarly, and the flamingo model implement they also use a pre-trained vision encoder and a pre-trained language encoder language models, and keep these two big models frozen. And they introduce a connection module, and there are two important modules in the connection module. One is a perceiver resampler. The main purpose is to reduce the computational complexity, and the other one is a gated cross citation layer plus a dense layer. And the major goal is to stabilize training in the initial stage of the training. So Flamingo has achieved a state-of-the-art performance on many academic research benchmarks. What I found the most fascinating about Flamingo is the multi-model in-context learning property. For example, when the model is trained, you can keep the model weights frozen. And if you have any downstream tasks, you can provide a couple or several examples as image test pairs and input, and those illustrate to the model that what type of task you actually want to perform in the inference stage. And then you provide your input image, and then the model will learn to complete a task based on the examples you provided. I think this Flamingo model is widely considered as the GPT-3 movement in the multi-model space. So now, earlier this March, and we see OpenAI release the multi-model GPT-4 model, right? So, and even though we don't know the model details, and in the paper, in the technical report, OpenAI has shown several visual examples in terms of understanding and reasoning, and we all found excited about the capability that GPT-4 is about to do. And so, for example, in the first, I think these two are popular examples now on the social media, right? So the model can do some high-level complex reasoning, and even though we are excited about it, and for a little while, the community, the open source community, have no clue that how OpenAI actually train this model and achieve such capabilities. And in this talk, I'll try to tell a little bit about my understanding how we could actually achieve these results. To better illustrate the gap between the existing models and the multi-model GPT-4, I use the language model history from the OpenAI GPT families. And here I mainly illustrate the most interesting properties, the emerging properties I found for, I personally found interesting for each generation of their models. And for GPT-3, it is in-context learning and chain of thought. And for ChatGPT and Instruct GPT, and the most important property to me is instruction following, but it's still in the language domain. And when it comes to GPT-4, there's one additional capability, which is allow image input. In the multi-model space, And we say that if we consider Flamingo is the GPT-3 movement in the multi-model space, now we also have multi-model GPT-4, and now there's gap, right? And what is the gap here, and how we could possibly fill this gap? To me, I think this is instruction following and how to do alignment research to fill this gap. Okay, we see that instruction tuning or instruction following capability is important, right? And so to explain, I start with language domain, because this is the notion of instruction tuning was designed first. So let's use some examples. Those are the in NLP community. How would people actually represent their data traditionally? So I provided 2 examples here. Overall, people will always represent their data as synchronous input and a synchronous output, right? So in these 2 examples, the first one is kind of translation, and second one is summarization. I did not provide any task instruction explicit here, right? But if you look at data, you already figure out that the task instruction for each of them. It means that in the traditional NLP setting, even though we have never explicitly specified the task instruction, the instruction is kind of implicitly specified by the data. And what people did is that they may train individual models on each type of data, right? And sometimes they will merge the data together and trying to do multitask training. Even with multitask training, they will never specify the task instructions in the training. It means that in the inference stage, it's going to be very hard for the model to know what type of task the model will perform, right? And with this, it makes the such trained model hard to generalize to unseen new tasks in the inference stage. Now it comes to instruction tuning. So instead of implicitly encoding this task instruction, for instruction tuning, it's actually expand the original data, right? Previously, we have the input-output data pairs. Now we expanded it to the instruction input-output triplets, and we augment the task instruction and put it very explicitly as a part of the training data. So, for example, in the first case, I'll add the instruction translated into the simplified Chinese, and in the second example, it's going to be summarized in 10 words of the input text, right? And those will be part of the this will be part of the training data for model training. Since we have explicitly specified the training, the instructions for each type of task, and then we put all of them together, and the model learns which task it will do in the training. And in the inference stage, we will also specify the task that we want the model to perform. And in this way, it makes the trained model easy to generalize to new task. I provide another example here. So let's say in the training, we only have the task for translation and task for summarization. And in the inference stage, so we provide a new task to the model, which kind of the task of combine the translation and summarization. And this task is never explicitly specified in the training, right? And because the model neural network can do a very good job in terms of generalization, and in this case, it's going to be task composition. And now it comes to the new task, and model can understand this new task well and complete this task. I think this is the intuition how instruction tuning works in the NLP. And this has been very successfully to make the model generalize well for their short and few short tasks. So now we have seen the power of instruction tuning, right? And how it can make model better generalized to the unseen new task. Then the problem is we see that the key is actually how we get the instruction tuning data, right? And to me, there are two different ways to get the instruction tuning data. And first one is a human to human interaction way. For example, if you provide it to some annotators, say, please provide such instruction for such data, and then you can spend a lot of money, and then you can spend a lot of time to get thousands of high quality instruction data, right? And so this is generally considered as the time consuming. And the other way is we can use the human machine interaction way to get the data in a more scalable way. And more specifically, I'll talk about the self-instructed framework to help us get the high quality instruction tuning data in the NLP first. Previously, remember, we have write our own instruction data. One is a translation example. The other one is a summarization example, right? We could actually use this as seed examples. And let's try to leverage the power of in-context learning in GPT-3 and the GPT-4. And so because we have provided these seed examples as illustration, and then we ask powerful language model to generate a diverse set of instruction and its corresponding responses. And in this way, we can iteratively connect a large number of instruction following data. And this is how self-instruct work in NLP. This idea has been very successful in NLP. And in the past several months, you may have seen the Llama family, right? Starting from the Meta Llama, and which is not instruction tuned, which is just a base language model, powerful language model. And to make it more instruction tuned, quickly in this community, you have seen a large number of llamas, right? So the people use different type of instruction data and tune their model, and then get their instruction tuned large language models. So there are many of them. I'll just list some of earlier versions. For example, Alpaca starting to use the teacher model. In Alpaca, the teacher model is GPT 3.5, and the famous Vicuna model considers shared GPT data, which is a high quality human and shared GPT data. And then the GPT Alpaca, instead of using GPT-3 as a teacher, and the authors use GPT-4 as a teacher. And there are many of them. And if you guys are interested in the most comprehensive way how to do self-instruct in the community, I will recommend this recent paper. The paper may be published a couple of weeks ago, and this one shows a very comprehensive way that how the model performance of this live research and how you do evaluation. Okay, and in terms of performance, and in the NLP community, people say that those instruction tuned data, they have shown a very good chat ability, and sometimes it's getting very, very closely to the chat GPT model, right? And it makes the community feel like with the open source tools, we could easily build chat GPT very soon. And so how about the multi-model space? So can we leverage the open source research tools and build a multi-model GPT-4 in an affordable way, in a more affordable approach? And today I'll use Lava as a running example, and I'll talk with you how we could create such instruction tuning data and how we train the model and what is the model performance. So in NLP, we have seen that self-instruct is very successful, right? That's because we have a very good teacher, where the teacher always takes in language input and output language as well. In the multi-model space, the question is, we don't have the public multi-model GPT-4 yet, right? We don't have a good teacher. And then there's a unique challenge. Now, how could we leverage this language model only teacher to construct a multi-model instruction volume data? That is a challenge, right? And in Llama, we provide an initial way how we could construct such data and train the multi-model chat agent. So let's first talk about the data. So even though we cannot feed the raw image into ChatGPT or GPT-4, right? Because those language models cannot understand image. And so alternatively, we can actually represent the image using its symbolic text representation. Think about bounding box, think about captions, think about whatever image understanding results we have had in the computer vision community, right? In the end of the day, we actually convert the image into some text representation or symbolic representation, right? So I think instead, this actually give us a way to represent the image into its text sequence, right? And in Llama, we specifically use the captions and the bounding box to represent the image. So now we could represent the image as the text, right? And now I think in this way we can still use self-instruct to construct high quality instruction following data. So what are the instructions we construct for the in the multi-model space? And in the future, you may build whatever instruction you are interested. And in Llama, we start with 3 preliminary instructions. The first type of instruction is a multi-turn conversation, because we want to build a chatbot, right? Where given the image, we can chat about it. And second type is the detailed description, where we want the model to describe the image as detailed as possible. And one goal when we build this model, we actually want to force the model to generate a long sequence. That's why we build this detailed description instruction. And as a last set of instruction following data, we construct the complex reasoning instruction. The reason is, remember previously, we have seen a couple of popular images from the OpenAI technical report, right? And the model, the GPT-4 model is actually able to reason over images, right? How about we reproduce those results? And so if we only use the previous 2, it's very hard for the model to reason over image, right? And so that's why we iterate several different versions, and it turns out complex reasoning instruction following data is very, very important. So let me give you one concrete example. And so for complex reasoning, it's not about the image content. It's more about the implications of the image. In this example, the image content is maybe a SUV in a parking area. And in terms of complex reasoning, we are asking the question, what challenge do these people face? And we see there is an SUV, there are many different luggage, right? And apparently the challenge is how could we actually pack all this luggage into this compact car, right? So with this machine generated instruction following data, we create a high quality instruction following data. And now let's talk about the model. And so in terms of architecture, it's very similar to all of the vision language model I mentioned earlier, right? So there are three modules. You have the pre-trained vision encoder, you have the pre-trained language. Oh, by the way, in terms of vision encoder, we use a pre-trained clip large. In terms of language model, we use the open source Llama, and we all and in terms of the collection module, we use a linear projection layer, and this is how we constructed the model, right? So in terms and now how did we train the model? This is a two-stage training procedure. In the first stage, we only update the projection layer and on the image text pairs. So the main goal of this stage is to align the two modalities. In other words, we could consider the projection layer is mainly doing visual tokenization, where you convert the image into the representations that the language model can understand. So in the second stage, we are going to update the projection layer and the entire language model on the instruction following data we have created previously. And so the main goal of this stage is to let the model understand different instruction, a lot of different tasks, so that in the inference stage, if you provide a new task, the model can do task composition, can finish this new task. Now let's talk about the performance. And we construct a small evaluation data set. And the takeaway message for this is that Llama model is able to achieve 85% relative score compared with GPT-4. And this is very close, but don't take it serious because it's a very small model on a very simple COCO images. And on the other hand, we also report results on established visual reasoning dataset called the Science QA. And the previous data is the multi-model chain of thought paper from Amazon. And so with Llama, we trained a second stage. We train our second stage on the training set of Science QA. And when we combine with GPT-4, it helped us to create a new state of art on this data set. Now let's see some examples. Remember previously I talked about the famous example, right? This image. And so with Llama, we actually just trained on a subset of COCO. And with this very small amount of training data, it turns out we could actually kind of reproduce the multi-model GPT-4 ability in terms of the complex reasoning, right? So the question is, what is unusual about this image? And the model is saying that there's a moving car and the man is doing ironing. Ironing is typically done inside the house, but now it is done in a moving car, right? This could be dangerous, something like that. And of course, if you are interested, you can continue to interact with Llama. We have a live demo online. And the second example, so besides the complex reasoning I have showed earlier, it turns out the model could also understand some of the text sequence in the visual image. And so if compared with the previous model, right? For example, belief tool or Open Flamingo, and those models, they are mainly trying to describe the image content because this is the single task the model is trained on, right? You cannot expect the model to doing more different tasks than its training. I'll show more examples after for Llama. So after we release the model and the demo, I trying to create some interesting examples for this model. And in this example, I upload the CVPR 2023 logo to Llama and ask who will be interested in the content in this image. And the model saying that there are two groups of people who might be interested. The first group is people living in Vancouver, Canada. And the other group is people who are doing AI and its applications, right? It means that the model can not only understand the text input, but also have some internal knowledge about what a CVPR is. In the second example, I upload the workshop, the computation in the wild. This is the workshop that in the first floor. If you guys interested in the afternoon, you can go attend this workshop as well. And this is a logo for our workshop. And so we ask what the image is about. And turns out the model can figure out that this is about the computer vision in the wild. And I also wrote llama by myself and uploaded to the image. It turns out the model can understand itself. This is a new word, by the way. So with llama release, so we have seen a lot of papers released in the past 3 months, right? Maybe on a weekly basis or sometimes daily basis, right? And the research pace is so fast nowadays. So we all start with motivated by some of the private models such as Flamingo and GPT-4, but luckily in the open source community, we have llama model released by Meta, and built on top of it, we have instruction-tuned language models such as Alpaca and Vicuna. So after Vicuna is released, in 2 weeks, mini GPT-4 and the Llama was proposed, and it actually enables those open source large language models to see and reason over the image. And in maybe 10 days, and there are newer models who are trying to compare with Llama and mini GPT-4. And it seems that in April, the data points are relatively sparse, right? But in May, we see a lot of papers, right? And personally, I was amazed by how hard work this community is. And in June, and we still have this trend going on. So there are a lot of papers, a lot of models, and also some benchmarks. For example, those with underline are the benchmarks proposed by the community. There are a lot of papers. I also try to summarize all the papers into different groups when I prepare for this tutorial. So you don't, if you want to, personally, I think I lost the track of all of papers before I prepare for this tutorial. And now, there are different topics. For example, multi-model in-class learning and trying to combine with established data sets, and also people try to include more modalities beyond vision and language. So I will try to highlight several topics. For example, more modality, right? So image bind is a work that uses the image representation at the center, and they are trying to include maybe video, audio, and other modality. And because all of these different modalities, they share a common latent space or picture space, and it's natural actually to extend the llama-like work to more modalities than vision and language. And then PetaGPT is such a piece of work that extend to more modalities. And we also have speech GPT, where the model can take input of image and speech and output text and speech. So remember, when we built the Lava, we mainly focus on the user-oriented tasks. For example, daily conversation. I have to remind you guys that in the NLP community, when people are talking about instruction tuning, there are maybe 2 groups of work. One is instruction tuning for user-oriented tasks, such as OpenAI models, and the other group is instruction tuning for academic research benchmarks. And so even though people are doing instruction tuning, and the goal is different. So when we build a Lava, our goal is mainly for user-oriented tasks. But in the research community, in the vision language community, there are a lot of academic research, and they are all about well-established vision language tasks. For example, captioning, BQA, right? You can also rewrite such data set in the instruction following format and join trained with the instruction following data. And instruction GPT, instructor belief is such a piece of work that combines these two types of instruction tuning data. So in Lava, the model is only able to take one single image as input, but in the multi-model space, sometimes we have the applications with the multiple image or video, right? And then it is necessary to have a model that consider multiple image input. And in this case, it's going to be multi-model in-class learning. And Alter is one piece of work in this line of research that allows multiple image input. And in the university labs, people are always complaining, say, we don't have enough GPUs to train such big models, right? And luckily in the research community, there's a live research called parameter efficient training, where they only have a small number of trainable parameters so that you can train your model with maybe 8 GPU or 1 GPU. And if you do have very limited resource, please check out the recent work from NLP community called QLaura. I think the most amazing thing is they could train a 65 billion llama model in 1 day with 1 GPU. So there are a lot of models, right? And how do we do evaluation? And there are benchmarks about the object hallucination, adversarial robustness, and OCR, and some of the recent benchmarks proposed maybe in the last 1 week. And the people are doing more and more serious research about this live research. So one thing I want to highlight is the OCR capability. So note that when we do Lava training, there is no OCR data in the training, but it turns out the model can do zero-shot task transfer for OCR, right? And there's a paper that trying to benchmark all the open source large multi-model models for their OCR capability. It turns out all the models, the zero-shot performance is worse than the state-of-the-art supervised trained SOTA in the OCR topic at this moment, but there's one data set that is different, that the zero-shot performance of the LMM is better than the supervised SOTA. This one is more about reasoning based on the OCR results. And lastly is application. So multimodal GPT-4 is popular, and we also see there are many vertical domains that require their own multimodal GPT-4, right? And medical is apparently one of the most important applications there, and there are papers trying to apply GPT-like models to the medical domain. And the LlamaMed is an extension of Lava, where you train 8 GPUs for maybe 50 hours. Then you get the LlamaMed model. And one interesting observation is, even for the original Llama model, the model is able to talk about medical image, but it's just like some other ordinary person like me. I know it is a medical image, but I cannot talk about the details with domain specific knowledge, right? if you ask me, for example, some clinical advice, I'll tell you I don't know. Similarly, Lava is doing that. But if you train the model on the medical domain data, then you will see that the model will trying to provide some helpful suggestions about the medical question. So we have a lot of open source effort trying to building or surpassing multi-model GPT-4, right? And so I would say that in terms of new capabilities, we may see a chance that the open source effort may sometimes surpassing multi-model GPT-4, right? Because multi-model GPT-4 is not able to do image captioning, image generation, and there is a work that is able to do image generation end-to-end with GPT-4-like model. But so I want to say that there is a large gap remains between the open source efforts and the true multi-model GPT-4, especially when we talk about the scaling success for a given capability. I'll give you concrete examples. So in a multi-model GPT-4 paper, we also show more complex reasoning results, right? For example, given a paper as input, ask the model to summarize the paper, and apparently it requires the model to understand multiple high resolution image, and it can handle long sequence, right? Sometimes when it responds, we require domain knowledge, and all of this it requires large training or more compute, and this is not affordable for most researchers. So what can we do next? I would say that for industry labs with resources, please scale up and study the emerging property. And for university labs, maybe we should consider something like a prototype, small prototype like Lava, to consider how we can enable new scenarios with new functionality or doing some evaluation. And to summarize, I show you some of the powerful capability of multi-model GPT-4 and how we could possibly build the mini version of the multi-model GPT-4 and some of the recent papers on top of them. And I'll release this slide deck on our tutorial website. Thank you.
We have one last talk, so if you are not too hungry yet, please stay. Thank you. Okay, so thanks to Ryan for the great talk on the large multimodal models. And in the last part of our tutorial, I'll be covering a very recent research topic, multimodal agents. Here is the overall structure of our tutorial again. And in this part, we answer the fifth question we brought up in the very beginning: how to train multimodal experts with large language model to enable multimodal agents. So first, let's revisit the evolution of modeling paradigm, especially in today's deep learning era. We started with training task-specific models and on small-scale, well-annotated data. And this leads to dedicated models for each task or even each data set. Then, for early foundation models, the pre-train and fine-tune paradigm can take advantage of large-scale, well-crawled, noisy data for pre-training. But the fine-tuning stage is still mostly task-specific on the same small scale, well-annotated data as the task-specific modeling. And this paradigm has become very popular in both NLP and vision language research. And we witnessed many well-known models, which used to be considered as large-scale models, but maybe more intermediate or even small size in today's view. And nowadays, we are entering a new era of generalist modeling, where the pre-training is done on extra large data. And for downstream adaptation, in-context few shot with a few demonstration examples or zero shot can do the job. We call these models large language or large multimodal models, including the GPT family, PaLM, PaLM-E, Llama, Flamingo, and so on. And going back to the instruction tuning covered by Chunyuan just now, the pipeline of building instruction following models can be still considered as a pre-trained and fine-tuned paradigm. So for example, for Alpaca, it is built on top of the pre-trained Llama and then tuned on instruction tuning dataset. Similarly, for VR models like Lava, an additional stage of image text alignment pre-training is introduced to align the visual representations to the frozen large language model, and then perform instruction tuning. So taking the advantages of large language models, researchers are now exploring a new paradigm that shifts from standalone models for solving finite predefined problems to synergistically chaining multiple tools or experts to solve complicated open problems. Note that the system can be built without any training involved. So just by taking the advantage of the power of large language models, giving it a few demonstration examples to teach it to generate proper calling of tools. The user will directly interact with the large language model, and based on the user intent, the large language model will plan on what tools to use and in what order. The tools can be open source models, public or private APIs, code interpreters, and the output from all these tools will be feedback to the large language model in text and summarized by it to as the response to the user. And this new paradigm has been previously studied in NLP to train specialized NLP tools to solve more complicated problems. For example, the NLP tools can be calculator, calendar, search engine, or specialized models for question answering and machine translation. And as shown in the table here, all those methods, they don't have image understanding capabilities. And inspired by the previous NLP text-only agents, just in the span of 3 months, we are seeing many works proposed to build multimodal agents to explore whether we can use large language models to train multimodal experts for more complicated multimodal understanding problems. And the multimodal agents displayed in this slide is just a glimpse into the fast evolution along this direction. And in this talk, we'll use MMReact as an example to show how we can train multimodal experts with large language model for advanced multimodal reasoning and action. MMReact leverages ChatGPT as the large language model, with chat as the user interaction interface, and can support both inputs and outputs in multiple modalities, including text, image, and video. In its design, it composes numerous vision experts with ChatGPT. And ChatGPT is the tool allocator, plans on which tools to use and in what order based on the input image and the user intent. The user intent can be a question like the one showing here, how many championship rings did the player on the left win in his career? And the next will show a breakdown of the planning and execution steps behind the scene and explain in detail how MMReact works. As ChatGPT only accepts language inputs, to enable image as input to ChatGPT, we simply use the file path as the input. The file path will function as a placeholder, allowing ChatGPT to treat it as a black box. So upon receiving this file path, ChatGPT will recognize, oh, it stands for image input. And next, to grasp a general understanding about the image, ChatGPT plans on what tool to use. For example, image captioning for an overall description of the image, dense captioning to get a reasonable, more detailed description about each object in the image, object tagging to get the object tags, and as the tags may mention faces, it further invokes face detection to get the bounding box coordinates of the two faces. And face detections may localize the faces in the image, but it doesn't recognize the identities of these faces. So celebrity recognition is called to get the names of these two persons. For each call, the outputs from the tool are serialized in text and feedback to ChatGPT for it to decide the next move. And when ChatGPT decides no external experts are needed, it takes the observation gathered from the calling of all the tools, a total of 5 showing here, and summarize it as the response to the user. Now, if the user asks, how many championship rings did the player on the left win in his career? It's not in the observation, but ChatGPT has the knowledge of the bounding boxes to decide who is on the left, and also the names of the player. It can take that information and invoke Bing search to find the right answer, which should be 5. So with the help of all these external experts, MMReact enables ChatGPT with more advanced capabilities for multimodal reasoning and action. For example, visual math and the text reasoning to solve math equations in the input image, understanding visual condition joke or memes, understanding spatial relationships between objects in the image or the bounding box coordinates, visual planning and prediction, reasoning over multiple image inputs, multi-hop document understanding, open word concept understanding, for example, product brands, celebrity, and food, video summarization or event localization. And we will be showing 3 examples to let you have a close look into the advanced capabilities of MMReact. So the first one is for multi-image reasoning. Imagine that you are a very organized person. You take a photo of the receipt whenever you make a purchase. MMReact can reason over multiple receipts and summarize your spendings. So in the example we're showing here, we upload 4 receipts one at a time. Each time when the MMReact receives the receipt, it first to recognize the text in the receipt image and summarizes the spendings shown in the current receipt image. After all 4 receipts are uploaded, we first ask a few simple questions with only 1 receipt involved. For example, how much did I spend on grocery? MMReact can correctly identify that the grocery spending is associated with the 3rd receipt image and return the total amount from that receipt as the answer. And similarly for the second question, only the last receipt is needed to answer the question. Then we try a level up by asking how much did I spend on travel? MMReact correctly identifies the flight ticket and the Uber ride should be categorized as travel and return the summation of the spendings on the first two receipts. And finally, we ask how much did I spend on paying taxes? MReact successfully find the amount of tax I paid from all the receipts. Note that for the grocery one, there is no tax shown. So a total of 3 tax items here. And the second scenario is for multi-round image editing. When equipped with image editing tools, MReact can enable dialogue-based image editing. Here we borrow the image of a squirrel holding a camera shown in the GPT-4 demo. We added one object in the image at a time. The edited images show a desired change from the previous input images while keeping the remaining part intact. And finally, we show how MReact can perform video analysis. We first upload a video of Kobe's last amazing 3 minutes in his NBA final game. The whole video is about 7 minutes long. And MReact first returns a detailed summary about the video. We then ask a grounding question. How did Kobe win the last 2 points to get 60? Explain and provide me with a short video highlight. The first half of the question, it only requires the system to explain it verbally, while for the second half, it requires temporal grounding to provide the exact start and end time when the 2 free throws happen. As you can see, the returned video highlight indeed captures the 2 free throws from Kobe. So, okay, with MReact as an example, we now have a basic understanding of how a multimodal agent works. Next, I'll cover the unique benefit of this new paradigm from 2 perspectives: extensibility of the large language model, the core part of the system, and extensibility of the tools. So the large language model in the system can be upgraded to a newer, more powerful model when it comes out with no sweat. We tested by upgrading ChatGPT in MReact to language-only GPT-4. And we use 2 testing examples from the GPT-4 demo. The first one is solving the physics problem from a textbook image. And with ChatGPT, we see that it returns vague problem-solving steps with no concrete answer. And if we upgrade the ChatGPT to language-only GPT-4, we can get exact same correct answer as the multimodal GPT-4. And another example is the coding with vision inputs. From a rough sketch of the joke website showing the multimodal GPT-4 demo, we tried this on MReact with both ChatGPT and language-only GPT-4. Both can generate runnable code to build that website. But while for the one with ChatGPT, it has less style formatting than the one with language-only GPT-4. And another observation that is hard to show here in the slide is that the button to reveal punchline is not actually working with the one from ChatGPT. And we should all believe that GPT-4 is not the ending for developing large language model. And we can always replace the large language model in this system with a stronger and more powerful model when available. And with STEM as the popular vision foundation model, so to speak, one can combine it with GPT to allow for more types of human interaction with the multimodal agents other than the text. Recall that in MReact, the user intent is all captured by the language, natural language inputs from the user. In intern GPT, by connecting the tool SAM with GPT, it allows for more ways to interact with the system. For example, via clicks, scribbles, and drawing bounding boxes. All these interactions are similar to human finger pointing, when us humans are having a conversation. And SAM may be one powerful tool to add. In general, the design of existing multimodal agents incorporates tool via a plug and play mechanism, allowing for adding even more tools. So for example, Hugging GPT is proposed to leverage all open source models from Hugging Face. And Chameleon incorporates not only Hugging Face models, but open source models from GitHub, plus Bing Search API, plus Python compiler. As a grand vision, taskmatrix.ai envisions that large language model or multimodal large language model can serve as the allocator to connect even millions of APIs and may enable even advanced applications such as office automation, AI of things, robotics, or AI copilots. There are also works on improving this new paradigm, mostly focused on the planning step. The previously mentioned multimodal agents all uses natural language to prompt a large language model for planning and to decide which tools to use. One can use programming language for more accurate execution. However, as the codes are still generated by a large language model, the problem of inaccurate tool using still remains. And a recent work, Assist GPT, tried to improve the accuracy in tool using via self-assessment. It adds a stage of inspection and learning into the system. And when the round of plan and execution is finished, the system inspects the outcome and determines whether the reasoning path of calling an API is a success or not. If so, it will automatically add this example as an in-context example to teach large language model to for more accurate tool calling in the future rounds. And another thread on improving accuracy in tool using is to combine this system with instruction tuning. One can generate a data set of instruction API pairs via self-instruct to tune a smaller large language model. And by composing tools from a more specific domain, this new system paradigm can also support diverse domain-specific applications. So like what have been mentioned by Zhenyuan in his part, we can compose image synthesis tools with object level, pixel level, or image level understanding tools, and have a data synthesis pipeline to provide diverse annotations on synthesized images. And when composing the large language model with robotic executors, one can enable robotic actions based on multimodal instructions. And when training a pool of audio models with large language model, Audio GPT can understand and generate speech, music, sound, and talking heads. And with tracking, captioning, audio understanding models, chat video enables ChatGPT to understand multi-channel videos. And finally, we envision future directions on this new paradigm, suggesting what more we can do to further improve the current system. For one, imagine if we have a completely new scenario without a robust tool to use. Can we create a tool based on the user need on the fly? In NLP, creator has explored to create tools for math reasoning by writing Python code. Instead of calling off-the-shelf math solver API like Wolfram Alpha. So in terms of multimodal agents, can we create tools that can process multimodal inputs? For example, leveraging pre-existent Python packages such as OpenCV. Or even one day, can we build a deep learning tool on the fly? And the second direction is retrieval augmented multimodal agents. This is inspired by retrieval augmented large language model. For instance, if we have a database with a product image and the price pairs, can a multimodal agent retrieve the corresponding price given when prompted with the a product image? And the third direction is for evaluation. Although we have seen successes in building multimodal agents, mostly by example demonstration in the paper. And can we have a systematic way to evaluate how accurate it is for this type of system to use multimodal tools? API Bank is a starting point to building such pipeline in evaluating tool-augmented large language models. And finally, still on the evaluation side, perhaps also relevant to the large multimodal model covered by Chunyuan just now. There are a few works already exploring this to evaluate the emergent capabilities of large multimodal models and multimodal agents. But this emergent capabilities, there are probably more to come. And also they are not either covered by existing benchmarks, or the long chatty output from these models are not suitable for today's evaluation metrics. And we may need to think about new ways or new benchmarks to evaluate these emergent capabilities. And as a summary, from the last two talks of today's tutorial, we have covered two directions on building advanced multimodal systems, all based on large language model. One is instruction tuning from the last talk, and the other is the tool using in this talk. These two directions have their own pros and cons. For one, that instruction tuning can enable an end-to-end model that directly interprets rich semantics in multimodal inputs. However, as it requires training, it requires data curation and computation resources, hence much more expensive. And when tuned with limited data, it will lead to limited capabilities in certain scenarios like OCR mentioned by Chunyuan. And for the other hand, for tool using, there's no training needed. We can leverage off-the-shelf abundant models, APIs, or code interpreters as the tool. However, as it doesn't require training, we see failures in invoking the right tool with the system. And also, if we chain large language model with weak domain experts, we see weak performances. And in addition, I want to bring up two more in-depth research questions. As we now have open source large multimodal models like Lava, can we replace the large language model in the system with Lava as the tool allocator? If so, what is the criteria to decide which capabilities can be solved by instruction tuning, and what other capabilities that require a tool to build such advanced system? And with this slide, I would like to conclude today's tutorial with a recap on all the content we have covered today. We started with the focus on image encoder that consumes visual data and discussed how to learn image representations via visual pre-training and vision language pre-training, and how to extend vision models with more flexible, promptable interface to build a unified vision interface. We then covered image generation that produces visual data with a focus on alignment. And finally, we made connections to large language models to build a general purpose interface from two perspectives: one, to train large multimodal models, and the other to train multimodal experts with large language model to enable multimodal agents. And I would like to thank everyone that's attending today from either virtually or in person. And I hope you guys learned something new today. And thank you. Yeah, if you have questions for the presenter, please come up. And I think we have everyone in the room. Yeah, thank you.
The best tutorial.
Thank you so much. Yeah, of all on the tutorial website.
Hi, so great talk. Quick question about the motion description generator. Which agent produced that? Or the second one, create some comments seeking on their purity.
Check.
These slides, like the motion.
Yeah. So this is not our paper, but you can check their paper for more details. But I believe that this is a dedicated one, like for the action recognition.
Action recognition. Also for the movie example, you showed the basketball, so that the detailed description task is also a human label, or it's also generated from one of the agents.
General. So we leverage like speech transcription and image capture, video capture, action. Those tools to generate text response to ChatGPT and ask them to summarize it.
But is that a very detailed task is a summary result from
ChatGPT.
Okay, so maybe not single model can generate that one.
Not yet.
Right.
But I believe like from previous session, he covered some model that dedicated training large multimodal model for video understanding. He somewhat can do that from instruction to me. But yeah, some high level thing maybe needs more data.
Yeah, thank you.
我按着一下这个。
这连讲3个小时，连讲30分钟。